Hey guys, I'm really excited about this because this is the start of everything you need to know for A-level maths. This is the pure section, and the lovely Miss Phoebe is going to be taking you through each skill one at a time. For every single skill in here, there is a much longer video going through each skill at 3 different levels, lots and lots of questions. So if there is one bit that you're not too sure about, go and watch the longer video where it's explained and lots of examples are worked through to help you ensure that you can do each of these skills. Over on my website, there are thousands of multiple choice questions just waiting to help you revise and make sure that you've got the confidence in these skills so that you can go into the exam and apply it when needed.
The laws of indices normally involve a base number, let's call that n, and something happening to the base number. So for example, them being multiplied together. Now with the laws of indices, we also have an index involved, so we might have the power a on our first n and the power b on our second n. And so the law is that if you multiply together the base number, then to simplify it, you can add the powers together. So let's have a look of an example of this in action. So you might have 7 to the power of 2 multiplied by 7 to the power of 3, and that can be simplified to 7 to the power of 5. Now there's laws like this for subtraction as well, and that's when you're dividing the base numbers. So you're dividing the base numbers, then the 2 indexes, the indices, they are going to be taken away. So again, looking at an example, you could have 3 to the power of 5 divided by 3 to the power of 2, and that would simplify to 3 to the power of 3, taking the powers away. We also have a version for multiplication, where you have your base number and you multiply a and b. And what that looks like is you'll actually have one base number in this situation. It's going to be to a power a, and then all of that is going to be to a power b. So if you've got a bracket and you've got basically 2 powers, you're going to multiply the powers together. So looking at another example, let's say we've got 4 to the power of 2, and then that is all to the power of 4, then altogether that's going to give us 4 to the power of 8. We can also have one where you divide the powers, and rather than writing this as division, it's probably going to be more commonly seen as a fraction instead. But fractions and divides are the same thing. Now let's say that a is the numerator and b is the denominator. So what does this look like? Well, we're going to have our base number. It's going to be to the power of a, and then it's going to be to the root b. So if we look at an example, if we have the cube root of a number, so let's say this number is going to be a 2, and 2 is to the power of, let's say, 6, then that will be equal to 2 to the power of 6 over 3. And then, of course, you can simplify that. 6 divided by 3 is 2, so that would end up being 2 to the power of 2. So always look for opportunities to simplify these fractions if you can. Now, there are a few extra details with laws of indices. So, for example, if you have a number to the power of 1, then that's just the same as writing a number. If you have a number to the power of 0, then that's equal to 1. If you have a number to a negative power, then that's the same as 1 over that number to the positive power. So looking at an example of this, if we had, say, 3 to the power of negative 2, that would be equal to 1 over 3 to the power of 2. And actually 3 to the power of 2 is 9, so that'd be equal to 1 over 9. So just like you can simplify the fractions, you can also simplify fractions in these cases and actually multiply out things if it's going to make it simpler. But for now, we'll just focus on the core rules. Now, I've used numbers for all my examples, but you can use algebra. So, for example, you could have a to the power of 2 multiplied by a, and it will be a to the power of 5. Or you could have a to the power of 2 with brackets, and then you could have, say, a b on the outside. And so that would be a to the power of, and that'd be 2 times b is 2b. So we can have algebra involved. We can also have a mix of letters and numbers. So, for example, we could have 3a squared times 4a squared. So you'd follow the normal rules and all the numbers. 3 times 4 is 12. Then you would follow the laws of indices for the indices. 2 plus 2 is 4. So 3a squared times 4a squared would be 12a squared. 3 times 4 is 12. 2 plus 2 is 4. If this happens with the brackets, be really careful. So you could have, for example, 2a to the power of 2, all to the power of 3. Now, you don't just do 2 times 3 is 6 and write 2a to the power of 6. That's the wrong answer. Because not only is the a being raised to the power of 3, so you do your 2 times 3 is 6, the 2 is being raised to the power of 3, and 2 to the power of 3 is 8. So be careful of that. You can also have multiple letters. So you could have a to the power of 2 and b to the power of 3 multiplied by a and then b to the power of 4. So you do the letters separately. A2 and a, that's 2 plus 1 is a to the power of 3. Notice there's no 1 on the a, but as we said before, anything to the power of 1 is just that number. Then do the same thing with b's. 3 plus 4 is 7. So we can have a combination like that. The last thing to watch out for is negative numbers. You can have double negatives, and that'll just follow normal rules. Double negatives you'll particularly find when you're dividing, because when you're dividing, you take away the powers, and sometimes one of the powers is negative. So be really careful double negatives there. And the other one is with the fraction, when you've got n to the power of negative a, you can turn that into a fraction, and you make it positive. This can happen also with a positive. N to the power of a would be 1 over n to the power of negative a. So you're not really making the fraction positive. What you're doing is you're flipping the sign on the power if you're turning it into a fraction. One last thing to look at is all of these have the same base number. Now let's say the base numbers are different. So let's say we have 7 to the power of 2 multiplied by 2 to the power of 3. Now because the base numbers are different, a 7 and a 2 rather than a 7 and a 7 or a 2 and a 2, then in that situation you can actually simplify it. What you could do though is say that, well, 7 to the power of 2 is 49 and 2 to the power of 3 is 8, which will give you 49 times 8, and that will give you altogether 392. So if you have the same base numbers, you can do simplification. If you don't have the same base numbers, the best you can hope for is change them into the values and actually just get a value for it. The same thing also goes with addition and subtraction. With these, we know we've got lots of multiplication, division, brackets, and roots. We don't have any rules for adding together the same base number or subtracting the base number. And that's because we're adding rules. And again, like the example I just did, if you're adding or subtracting, the best you can hope for is turning them into the values and working it out that way. We have a few laws with surds. So for example, if you have a root, let's say root A, and you multiply it by, let's say, root B, then you can simplify that into the square root of A times B. And the same thing will work with division. If you got the root of A divided by the root of B, or written as a fraction, that's the same thing as the root of A divided by B, or again, written as a fraction. So let's look at some examples. So let's say we had the square root of 9 multiplied by the square root of 7, then we could say that altogether that's equal to the square root of 63. If we had the square root of 100 over the square root of 4, then we could say that is equal to the square root of 100 divided by 4. And actually just write these out with a little bit more detail. So then that would be the square root of 100 divided by 4, which is the square root of 25. You can also have laws for addition and taking away. Now these are with the same base root. So we had, say, a lots of root n plus b lots of root n. Then that would give us a plus b lots of root n. Now the general term looks pretty confusing, but let's have a look at an example. So if we had 3 lots of root 7 plus 2 lots of root 7, then all it means is that would give you 5 lots of root 7. And the same thing would work with subtraction. Now you can also simplify surds. So for example, the previous answer we got root 25. Well, we can find the square root of root 25. 25 is a square number. 5 times 5 is 25. Another way we can simplify is in the first question, we had root 9 times root 7. Now there's another way of writing that. Root 9, we can work it out. Root 9 is 3. So we could have written 3 times root 7, which would have given us 3 root 7. So that would be a lot simpler than writing root 63. We're using smaller numbers. In fact, what you can do is work backwards. You might be given root 63 as a question, and you have to recognise that 63 is a square number multiplied by something else. It's 9 times 7. And then you can change the 9 into the 3, and then you can write your 3 root 7 that way. So that first example, you can also be working backwards through that. Also with surds, we have something called rationalising the denominator. So let's say we had 33 over root 11. That looks okay, but we don't like to have roots on the bottom of a fraction. So what we do is, using equivalent fractions, we take the 33 over root 11 and we would multiply the denominator by root 11 and the numerator by root 11. Now, why we multiply by those numbers in particular? Well, if you multiply a root by itself, you're going to get just that number. So root 11 times root 11, you're effectively squaring it. And if you square a root, it cancels out. So that leaves you a number over 11. And then on the numerator, we're going to have 33 lots over root 11. And so that's a better form to have, because with a lot of maths, you don't want a irrational number for your denominator. So you might be asked to get rid of it. And let's just make a note at the top. If you've got, say, root a multiplied by root a, then that will give you a. Another thing to watch out for rationalising the denominator is that we can actually do the division here. We've got 33 over 11. 33 divided by 11 is 3. So that will give us 3 lots over root 11. Another thing to look out for when rationalising the denominator is you might have something like this, and the denominator might be some brackets with a surd in it and with a number with it. Now, with this, you can't just multiply through by root 3, because you multiply the 1 by root 3, which will leave you the root 3 at the bottom. So again, we'll just take our numbers. It might even be that you see the question without the brackets, actually. When you're doing the working out, put the brackets in, and you want to multiply it by a negative version of the same bracket. Now, what that does is, when you expand this quadratic, and you can have quadratics with surds, and just be careful when you're multiplying a surd by a number. You know, root 3 times 1 is 1 root 3, and root 3 times root 3 will give you just 3. So be careful of things like that. But what this would do is, for the numerator, we'd have 2 times root 3 and 2 times negative 1. So that's fairly simple. But with a quadratic, again, do you kind of 4 terms of multiplication? Root 3 times root 3 will give us 3. 3 times negative 1 will give us negative 1 root 3. 1 times root 3 will give us a positive root 3. And then 1 multiplied by negative 1 will give us negative 1. Now, when you get this, what you'll notice is the middle 2 terms will cancel out to give you 0. And you're also probably going to have 2 number terms on the denominator. So the numerator will stay 2 root 3 minus 2, but the denominator, the negative root 3 and the positive root 3 cancel out. Then we have 3 take away 1 is 2. And then we can even simplify that, because we can actually divide both terms by 2. 2 lots of root 3 divided by 2 is 1 lot of root 3. And negative 2 divided by 2 is negative 1. Now, you can't always do that, but always look out for situations where you can do that. When expanding brackets, we'll go through a few examples. So you might have something like a linear expansion, where we have one bracket. So, for example, 2 lots of 3x plus 1. And the way to do this is multiply the 2 by the 3x, which will give us 6x, and then multiply the 2 by 1, which will give us 2. It's really important to multiply by both, because a common mistake is only multiplying by one of those. You might have a letter on the outside, like x, and on the inside, you might have 4x plus another letter y. So again, the same method, x times 4x. Look at the numbers first. Well, we've only got 4. Then look at the letters. We've got 2 lots of x. That's x squared. Then we do x times y, and we can't do x times y. We don't know the values for them. So if you can't do something, you just leave it as it is. X times y, just write x, y. Then you can have a quadratic expansion. So we might have something like 5x plus 2 and 9x minus 3. So again, multiply the terms together. 5x times 9x. Look at the numbers first. 5 times 9 is 45. Then look at the letters. X times x is x squared. So you can do them separately. Then we do 5x times negative 3. Look at the numbers first. 5 times negative 3 is negative 15. And then we've got an x in there as well. Next, we're going to do 2 times 9x, which will be 18x. And then 2 times negative 3, which is negative 6. So they are the 4 multiplications you're going to do. The first term in the first bracket is multiplied by both things in the second bracket. Then the second term in the first bracket is multiplied by both things in the second bracket. Now I'm just going to write the answers underneath for a bit more space. And what you'll find with quadratics is often the middle 2 terms can be simplified. Negative 15x and a positive 18x. So 18x take away 15x is 3x. So our final answer would be 45x squared plus 3x take away 6. And we can't combine the x terms the x squared and the x, they stay separate, and we can't combine things with x and normal numbers. So we have 3 terms for our final answer. Other things to look for, quadratics with surds involved. So we could have x lots of root 7 plus 5 all squared. Now the squared symbol means we're going to have this bracket twice, and then we can do our multiplication. So x root 7 times x root 7. So what's going to happen there is we're going to have the x times x, which is x squared, and then the root 7 times root 7. Now, if you multiply a root by itself, it's going to cancel out the root symbol because you're squaring it. So that'll be 7. So it'll be 7x squared. Then we do x root 7 times 5, which will give us 5x lots of root 7. Then we'll do 5 times root 7. So actually that's the same multiplication. That gives us another lot of it. Then at the end, we'll have 5 times 5, which is 25. Now, again, it's a quadratic, so often the middle terms will simplify. We've got 5 lots of x root 7, and then another 5 lots of x root 7. So altogether, we've got 10 lots of it. So our final answer is 7x squared plus 10 lots of x multiplied by root 7, and then our 25. One last thing to look out for is a cubic where you have 3 brackets. So let's say we had x plus 1, x plus 2, and x plus 3. Now the method here is to start it off like a quadratic and only look at the first 2. So I'm going to highlight the first 2 and multiply them out. X times x is x squared, x times 2 is 2x, and 1 times x is 1x, that's 3x altogether, and 1 times 2 is 2. And then once you've got that, then you can multiply that by the third bracket. And again, you're going to use the same method, you've just got 3 terms this time. Now I'm not going to draw the arrows here, but I'm going to do x squared times x is x cubed, and then I'm going to do x squared times 3 is 3x squared. So that's the first term ticked off. Then we do the second term, 3x. 3x times x is 3x squared, and 3x times 3 is going to give us 9x. That's our second term done. Now we do the third term. 2 times x is 2x, and 2 times 3 is 6. Then all we need to do is add all of that together to get our final answer. And all those terms together, we've got our x cubed term, we've only got 1. We've got 2 x squared terms, 3 and 3, which is 6x squared. We've got 2x terms, 9x and 2x, which is 11x. And the number term at the end, the plus 6. So again, if you see a cubic, pretend it's a quadratic, multiply it with the first 2. Once you get that answer, then write in your third bracket and pretend it's a quadratic again and multiply through again. So it's basically a cubic is 2 quadratics in a row. For quadratic equations, you might have something like x squared minus 2x minus 24. And the task here is to put it into double brackets. So we need to factorize this. Now we know that x times x will give us x squared. We need to think about how to get the negative 24. Now a good technique for this is to list the factors for 24. So you can divide it by 1, 2, 3, and 4. You can't divide it by 5. And while you can divide it by 6, we've already written that down, so we've finished our list. And just note that I went through all the numbers one by one to get a complete list of factors. I didn't jump around randomly. Now, we want 2 numbers which multiply together to make 24, but they're going to add together to make a negative 2. So we have to look through our list and think, well, which ones of these, since they all make 24, which pair of numbers could make a 2? And it looks like it's going to be the one at the bottom. 4 and 6 could make a 2. And how does 4 and 6 make a 2? You would have a negative 6 and a positive 4 to make a negative 2. So now it's factorized. An additional question might be something like having it as an equation equal to 0. And to figure out what x would be if it's all equal to 0, you simply have to make x equal 0, or rather one of the brackets equal 0. So for example, with the first bracket, if x was equal to 6, the first bracket would read 6 take away 6, which is 0. And that'll make the answer equal to 0, because no matter what the second bracket would be, and it will be 2 in this situation, 0 times 2 is 0. In the same trick with the second bracket, x would have to be negative 4 to make the second bracket be 0. It would be negative 4 plus 4, which is 0. And then no matter what the first bracket is, I think that'll be negative 10. Because you're multiplying by 0, you're going to get a 0. You can also have quadratics, like this one with a coefficient on the x squared. So 3x squared minus 12x minus 15. So again, we want to get double brackets. You want 2 numbers which multiply together to make negative 15 as the numbers in those brackets. And for the x terms, well, the only option is 3x times x will make 3x squared. So let's have a look at the factors of 15. So we could have 1 and 15. We can't divide by 2. We can divide by 3, that'd be 3 and 5. And we can't divide by 4, so we've finished our list. So how can we get a 12 from those numbers? Well, we can. But another trick is, because we have a coefficient on the x squared, the 3, and that's found its way into one of the brackets, that's actually going to multiply the second bracket by 3. And if we're multiplying the second bracket by 3, then we're allowed to multiply one of our factors by 3. So let's have a look at our options. We could multiply the 1 by 3, or we could multiply the 15 by 3. We can multiply the 3 by 3, or we could multiply the 5 by 3. Now, which of these options is going to give us a negative 12? It looks like we've got a couple of answers here. We could have 3 and 15. We've got 3 and 15 either way, actually. So what's going to happen with 3 and 15 is you have to think about where these numbers have originally come from. So I'm not going to write 3 and 15 into the brackets. I'm going to write the original numbers, which for the first option is 1 and 15. Now, because the 1 is multiplied by 3, that's going to be in the opposite bracket. And so it would look like that. Then what a negative 12, so that'll be a negative 15 plus something to get up to 12. If we looked at the other option, and you can have multiple answers sometimes, then with the 3 and 15, it was actually the 15 was multiplied from the 5 times the 3. So the 5 would have to be in the opposite bracket to 3x to get up to 15, with the 3 staying as it is. Then again, for this, the largest one's going to be negative. So it'll be negative 5 and a positive 3. Now, interestingly, when you have multiple answers, when you're solving it equal to 0, you'll always get the same answer. So for the first set of brackets, 3x plus 3, that means that 3x would have to be negative 3. And if 3x is negative 3, divided 3 by 3, x would have to equal 1. Now, you'll also notice that the second bracket of the first option, if x was negative 1 there, that would also give you 0. So 2 of the 4 potential brackets can give you negative 1. That means the other one would have to be a positive 5 for the second bracket of the second option. But again, the first bracket of the first option, if x was 5 there, that would also give 0. Now, both of those examples had 2 answers for x. But you can have 1, 2, or 0 answers. And the way you can figure it out is using something called the discriminant. The discriminant is b squared take away 4ac. So let's have a look at some examples. So let's have a look first at the x squared minus 2x minus 24 that we started with. A is the coefficient on the x squared. In this case, it's 1 if there's no number. B is the coefficient on the x, and C is the number at the end. So b squared will be negative 2 squared, take away 4 times a, which is 1, times c, which is negative 24. That's going to give 4 take away a negative 48, which altogether is going to give us 52. Now, what does this tell us about the number of roots? Well, we're going to leave that for a moment and come back to this. Let's have a look at another example. So let's have a look at x squared plus x minus 8. So get a, b, and c are going to be the same things. A is the coefficient on the x squared, b is the coefficient on the x, and c is the coefficient at the number on the end. So b squared would be 1 squared, and we're taking away from that 4 times a, which is 1, times c, which is 8. Altogether, that's going to give us 1 take away 4 times 1 times 8. That's going to give us 32. So altogether, it's going to be negative 31. Okay, so that's a negative number. Now, again, I'm not going to explain what that means. Look at one more example, then we'll explain all three together. Now we're going to have a look at 4x squared minus 4x plus 1. So we have b squared, that'll be the negative 4 squared. Again, the term on the x, taken away 4 times a, which is 4, and c, which is 1. That gives us 16 take away 16, which is 0. And now we can talk about what all these mean with the discriminant. So if you have a positive, like in the first example, let's write positive as if it's greater than 0. That means, therefore, we are going to have 2 roots. We have 2 answers for x. If it's less than 0, like in our second example, that means we have no roots. There is no way that you can factorise x squared plus x plus 8. And finally, if we are equal to 0, then what that means is there's going to be 1 root. There's only going to be 1 answer. So when you have your factorisation, you've got your 2 brackets, you'll find that both brackets have actually got exactly the same number in them. And then that means that you only have 1 answer. Another formula is the quadratic formula. And the quadratic formula is negative b plus or minus, so you've got to do it both ways and get 2 answers, the square root of b squared minus 4ac. And you'll notice that's the discriminant. And that's why a negative discriminant means there's no answers, because you've got a square root of a negative number, you can't do it. And that's all over 2a. With the a, b, and c coming from the same source as they were for the discriminant. A, the coefficient on the x squared, b, the coefficient on the x, and c is the number at the end. Now you can substitute into quadratic formula, and that should give you your answers. So if we have a look at an example, let's do our first question again and see we get the same answers. So for our first question, negative b would be a negative 2. So we do have double negatives quite a lot here. Then we have the square root of b squared, which is negative 2 squared, minus 4 lots of a and c. So 4 times 1 for a, and times negative 24 for c. All of that is going to be divided by 2 lots of a, so that's 2 lots of 1 is 2. Now, negative 2 is 4, so it's 4 plus or minus the square root of, now we worked out the discriminant for this already, and it was 52. And then we divided everything by 2. And actually, looking back, that 52 was wrong because I multiplied by 2 and I should have multiplied by 4. So actually, 4 times 1 times 24 would be 96. So then when we add the 4 to it, that's going to give us 100. Now, 100 makes more sense, actually, because then that is a square number, and that means we can simplify this nicely. So I knew this was wrong straight away because the root of 52 wouldn't actually give me whole number answers. Now, if we work this out, 4 plus root 100, which is 10, is 14 divided by 2, which is 7, which isn't one of the original answers I've got. So I know I've made a mistake somewhere, either with the original question or my work in here. I'm just looking through things I've noticed. Negative 2 ended up being a positive 4. Now, actually, negative 2 is just going to be a positive 2. So now it's going to make more sense, because now I have 2 plus root 100, 2 plus 10, which is 12, which divided by 2 is going to give us the 6 that we have in our final answer. Then once we try it with a plus, we try it with a minus. 2 take away root 100, so 2 take away 10 gives us negative 8. We divide that by 2 and we get the negative 4 we had in our original answer as well. Now, if you did this and then the root wasn't a square number and you'd be getting a decimal when you rooted it, then you've got 2 options. You can either work it out and have a rounded decimal answer, or you can actually just leave your answer as 2 plus or minus root 100 over 2, or the equivalent of something that couldn't be simplified. And that should be fine as well, unless you've been asked to provide 2 roots or equivalent, and you've maybe been given what to round it to. We are going to go through a few different ways of solving simultaneous equations. And by simultaneous, what we mean is we're going to have 2 equations. So we could have 2x minus 5y equals negative 14, and 5x minus 4y is equal to negative 1. So we have 2 equations. The reason why we have 2 equations is that we can't work out what x and y are unless we have 2 of them. So we've got 2 variables, we need 2 equations. Now, the way to solve this is we need to make the coefficient so that either x or y be equal. And the only way to guarantee that is to multiply them by each other. So let's say we're going to try and make the x's be equal to each other, the 2 and the 5. Multiply the 2 by the 5 and the 5 by the 2. And when you multiply, make sure you multiply all the terms. So 2x times 5 is 10x, and negative 5y times 5 is going to be negative 25y. Then negative 14 times 5 would be negative 70. Then do the same thing with the second one, but this time we times them by 2. 5x times 2 is 10x, negative 4y times 2 is negative 8y, and negative 1 times 2 is negative 2. So what we've done now is that we've made the x terms be equal. They've both got the same coefficient. So now they have the same coefficient, we need to cancel them out to get 0. And the way we do it this time is by taking them away from each other. 10x take away 10x is 0. Sometimes you have to add, and that's when the signs are different on them, but in this case they're both positive, so we can take away. So taking away the 10x away from each other gives 0. Then negative 20y, take away negative 8y, altogether it's going to give us negative 33y. Or a little that way, but I have made a mistake. Now, if you look at this more carefully, it's negative 25y take away a negative 8. So we've got a double negative, so it's not actually negative 33. We're going to be adding 8 on, which is going to give us negative 17y. So now we've taken away 2 terms. Now we take away the third term, which is negative 70. Take away a negative 2. Again, that'll be double negative. Gives us negative 68. Now, negative 17y equals 68. That is an equation we can solve. We can divide both sides by negative 17. So negative 68 divided by negative 17 gives us 4. So y is equal to 4. Now that we know that y is equal to 4, we can find what x is, and we do it by substituting into one of the original equations. I'm going to choose the bottom one because I think it's got smaller numbers overall, so it doesn't matter which one we choose, it's the same answer either way. So 5x minus 4y equals -1. So we know that y is 4. We can say that 5x take away 16 is equals -1. And then we can solve that. So we can add 16 to both sides, giving us that 5x is equal to 15, and divide both sides by 5, so x is equal to 3. The last thing you should do is record your answers really clearly. So x is equal to 3, and y is equal to 4. So we've done a few steps here. We have equalized one of the variables, either x or y, either's fine, and you do that by multiplying them by each other. Then we've done an add or a takeaway to cancellate that variable. In this case, it was a takeaway, and we solved the equation. Then we substituted into one of the original equations with the number we just got, y equals 4, and then we solved that. So altogether, we're doing around about 5 things here. Other examples to be aware of are things like x squared plus 3y equals 15. So we've got a squared sign in this one. Then we have one without a square sign, x plus y equals 5. So another way to solve these is by substitution. What we can do is we can rearrange this to make y the subject, and we can say that y is equal to 5 minus x. And we can substitute that into our original equation. So we've got x squared plus 3 lots of y, and we know that y now is 5 minus x. So if we expand the brackets, we get x squared is equal to the x term first, 3 times negative x is negative 3x. Then the number term, 3 times 5 is 15. And then we can take 15 away from both sides to get it equal to 0. And if we do that, we're actually going to get it equal to 0 without a number term on the left-hand side. Now we have a quadratic, and by working out the quadratic, we're going to get our answers. Now, if we factorise this quadratic, because there's no number term at the end, we're just going to take x out. So I divided both terms through by x. So to find out what x is, we want it all to equal 0. So if x was 0, that would give us 0 times what's in the bracket, which is equal to 0. Also, if x is equal to 3, then the bracket itself would be 3 take away 3 is 0, and then you multiply that x by 0. So there's 2 different ways to make this equal to 0. All we do now is substitute those numbers into our original equation. That would give us 0 plus y is equal to 5, and it would give us 3 plus y is equal to 5. That means that y would have to equal 5, or y would have to equal 2. At the end, writing final answers, our first set of answers was x being equal to 0 and y being equal to 5, and our second set of answers was x being equal to 3 and y being equal to 2. The last thing to be aware of is that you can do this as well with kind of line equations. So for example, if we said y is equal to 2x minus 7 and y is equal to the square root of negative 2x plus 9, what we could do with these two is that we could combine them together. They're both equal to y, so we make them equal to each other. And that would give us 2x minus 7 is equal to the square root of negative 2x plus 9. And then now they're equal to each other, you can rearrange them, and then that's going to give you a quadratic. Because our first step is going to be to root both sides, or rather square both sides to get rid of the root. That would give us 2x minus 7 squared is equal to negative 2x plus 9. Now, I'm not going to do the rest of this because we've seen this already. We'll rearrange it, get our quadratic, and it's like the last example. You're probably going to get 2 answers for x, and once you get 2 answers for x, you substitute into one of the original equations to figure out what y is. We are going to have a look at how to factorise a cubic, and the one we'll look at is x cubed minus x squared minus 8x plus 12. And so what we want from this is we're going to want 3 brackets that all multiply together, and they're going to make this number. So, for example, for the x cubed, we know that must be x times x times x. But then for the extra numbers, we know that the numbers multiplied together must be the 12. But there's different ways of making the 12. We could have 6 times 2 times 1. We could have 3 times 2 times 2. There's lots of different ways of making it. And we don't really want to use trial and error and expand out lots and lots of brackets. So we need to use a simpler method. Now, we are going to use a little bit of trial and error, and the way we do this is using substitution. And we need to guess what our first factor is going to be. You'll see why in a moment. So let's guess that our first factor is going to be when x is equal to 1. If we substitute that in, we get 1 cubed, take away 1 squared, take away 8 lots of 1, plus 12. Now, if that equals 0, then we have a factor. So we have 1, take away 1, take away 8 plus 12. Altogether, that actually gives us 4. That means that 1 is not a factor. So now we could try -1, or we could try positive 2. So that'll be for 2, 2 cubed, take away 2 squared, take away 8 lots of 2 plus 12. That will give us 8, take away 4, take away 16 plus 12. And altogether, that does give us 0. That means that 2 is going to be one of the answers. And so if x is 2, then we're going to have x minus 2 in one of the brackets. Because when we say it's equal to 0, if this whole thing was equal to 0, then x being equal to 2 would mean that our first bracket is 0, because it's 2 take away 2, which makes the whole thing equal to 0. So now we know one of our factors. Now we can use a method to find the other 2 factors, and that method is algebraic long division. So we're going to take our factor, x minus 2, and we're going to divide our expression by it. So that's x cubed, take away x squared, take away 8x plus 12. So we use algebraic long division. So the way this works is we can't really divide through by x minus 2, that's a bit too complicated. We're only going to divide by the first term, the x. I'm going to do each term one at a time. Look at x cubed first. So let's divide. X cubed divided by x is x squared. Now that's not actually our answer because we didn't divide by the -2. So what we do now is we multiply the x squared by our original divider. X squared times x is x cubed. And then x squared times -2 is -2x squared. So what that means is we didn't actually get the -2x squared out of this. So now we can include it. So by doing that division, we've accounted for part of the expression, x cubed take away 2x squared. So we take it away now from the full expression. Now the first 2 terms will calculate to make 0. Then we have -x squared take away a -2x squared. And if you take away double negative like that, that'll be -x squared plus 2x squared, which would be a positive x squared. And the rest of the expression is having 0 taken away from it, so it stays the same. So we divided by our first term, and we've seen what's left over. Now we're going to divide our brand new second term, not the original second term, but our new one, by x. So x squared divided by x will give us 1x. Then, of course, we didn't divide by the -2, so we multiply it to account for the -2. X times x is x squared. X times -2 is -2x. And then we take what we found away from what's left over of our expression. First 2 terms cancel out to make 0, and then -8x, take away -2x, double negatives I can add. That actually gives a -6x, and then we've got the plus 12 that we've taken nothing away from. So that's our second term dealt with. Now we look at the third term. Now it's the third term from our new expression, -6x, and we're dividing it through by the x. So -6x divided by x is -6. Then again, we didn't divide by the -2, so we've got to account for that by multiplying by it. -6 times x is -6x, and -6 times -2 is a positive 12. If we take those away now, we get 0. And if you get 0, you have no remainder. That means that x minus 2 does actually divide into x cubed minus x squared minus 8x plus 12, and therefore it is a factor. So it's kind of proven what our substitution showed us earlier on. Now, what that leaves us with is this. We know that x minus 2 is a factor, but also the answer to the division is a factor. X squared plus x minus 6. And now what we can do is, our first bracket's fine, but our second bracket's a quadratic, and we can turn that into 2 kind of linear brackets. So now you just use your factorising quadratic skills. Now, a -6, you want 2 numbers which multiply together to make 6, and they're going to add together to make a 1x. Well, 2 times 3 would make 6, and then to get a +1, we do +3, take away 2. So we're just using our factorising quadratics using inspection skills. And there's our Factorise cubic. It's x minus 2, and an x plus 3. We can even simplify that. We've got 2 lots of the first bracket. We can give a little square sign there, and then write our third bracket afterwards. Functions is something we can use for substitution, for example. So we have the function, which we call f of x, a function of x, and we say it's equal to 3x plus 5. Then if we want the function of, let's say, 5, then we swap all instances of x with 5. That'll be 3 lots of 5 plus 5. 3 times 5 is 15, and plus 5 is 20. So that's the primary use of functions. Now, there's some things with functions that you need to be able to do. So the first thing to do is substituting into functions multiple times. So let's say we want to find f g of 3. Well, what could that mean? Well, if we say that g of x is equal to 11x and f of x is equal to x plus 3, now we've got two functions that we can look at. So we've got the function of x, x plus 3. Then for g of x, it's not f function, but we can't use the same letter or everything. So it's just another function, 11x. So to find gf of 3, what we do is we start with the inside. We start with the letter that's nearest the number we're substituting, which is the f. And so what we're going to do first is work out f of x. And that's going to give me f of 3, which is 3 plus 3, which is 6. And now from f, next we do g. And it's going to be g of our new number, our new answer, which is 6. And g of 6, that's going to be 11 times 6, which is 66 for our answer. So to substitute into multiple expressions, we start off with the expression that's nearest the number we're substituting. We'll do f first, and then we do g. Now, we can also find an expression that kind of is g of f of x. We can combine them together without doing a substitution. Now, the way we do that is we're going to start off with the outside with g, and g is 11x. But what we're going to do is we're going to swap the x with the function f, which is x plus 3. Now, if we substitute into that and substitute 3 in, we still get 66. So let's test it. So gf of 3, that'll be 11 lots of 3 plus 3. 3 plus 3 is 6, and 6 times 11 is 66. So that method does actually work. So we've looked at just regular functions and substituting in, and we looked at composite functions where we combine multiple functions together. The next thing to look at is inverse functions. So let's say we have a function of x, and it's x minus 9 all over 6. Now, we can find the opposite of this. So if we put a number into this and got an answer, let's say x was 10. Then we'd have 10 take with 9 is 1, and 1 divided by 6 is 1/6. So we get 1/6. Now, the inverse function is a function where we put in 1/6 and we get 10 out the other side. We work the opposite direction. Now, the method to do this is, firstly, translate this into a kind of line equation almost. So y is equal to x minus 9 over 6. And then once you've done that, flip around the two symbols. So x and y are going to be the other way around. So that will give us x is equal to y minus 9 over 6. And now it's inverse, let's rearrange it to make y be the subject. So we can multiply both sides by 6. That will give us 6x is equal to y minus 9. And then we can add 9 to both sides. And that will give us 6x plus 9 is equal to y. And once we get to that stage, all we do now is we swap y back for f of x, but this time we'll f to minus 1x, showing it's an inverse function, which is what the negative one does. The inverse function is 6x plus 9. So remember our example earlier, if we substitute 1/6 into this, we should get 10 out the other side. So if x was 1/6, we'd have 6 lots of 1/6, which is 6 over 6, which is a whole one. And 1 plus 9 is 10. So it checks out that's actually going to work. So let's run through the kind of things we've done. We've done substitution with functions. We've done composite functions. We combine multiple functions together. And we have done inverse functions. So there's 3 different types. Partial fractions is about taking an expression, let's say 12x minus 8, all divided by x squared minus 5x minus 24, and changing it, rather than being one fraction, changing it into being 2 fractions. Now, the way you change it into 2 fractions is all about how you factorise this. So your first job is to factorise. Now, factorising the numerator, you can take 4 out as a factor, and factorising the denominator, it's a quadratic. So you can put it into double brackets, and we should have x plus 3 and x minus 8 when you factorise a quadratic, using whatever method you like. Now, once you have that, now we can see the fractions we need. Again, it's still one fraction, but our new fractions are going to have x plus 3 and x minus 8 as denominators. But then the numerators, we don't know what they are going to be. So let's call them A and B. Now, we're going to have to try and simplify that. And so what I'm going to do is I'm going to write everything out again. So I've got some working out space because I'm going to be drawing all over this and doing lots of crossing outs all over this. So I want the left-hand side written out again. We also want the right-hand side written out again. And what we're going to do is try and get rid of the fractions. That's our first step. So what we want to do is multiply through by all the denominators. So we have x plus 3 as one of the denominators. So we're going to multiply all three terms we have here by x plus 3. Then the other denominator is x minus 8. So we're going to multiply everything by x minus 8 as well. Now you might think, well, what's the point of this? Because we haven't got rid of the denominators. But then we can simplify through. We can say, well, x plus 3 divided by x plus 3 is 1. And so they cancel out. When you multiply the numerator by 1, it's going to stay the same. And x minus 8 divided by x minus 8, that will cancel out as well. We do the same thing on the right-hand side. We've got x plus 3 and x plus 3 cancel out, and x minus 8 and x minus 8 cancel out. So only two of the brackets that are multiplied through by are still going to stick around. And what that's going to give us, if we then write this out again, is 4 lots of 3x minus 2. And that's all that's left on the left-hand side. And on the right-hand side, we're going to have a lots of x minus 8 plus b lots of x plus 3. Now, we can substitute in values of x to get rid of one of the variables, because we can't solve equations got an a and a b in. We need to get rid of one of them. So we need to substitute in two things. To get rid of a, x would have to equal 8, because then the bracket will be 8 take away is 0, and a times 0 is 0. So if we said that x was equal to 8, that would give us 4 lots of 3 times 8, take away 2 on the left-hand side. And on the right-hand side, the a bit's gone. So we've got b lots of 8 plus 3. And then you can work that out. So on the left-hand side, 3 times 8 is 24. Then we take away 2 to get 22. And we multiply by 4 to get 88. That's equal to 8 plus 3 is 11, so that's an 11b. So b must be equal to 8. So this is when we got rid of a and we got b. Now we need to get rid of b to get a. Now in the b bracket, we have a positive 3. So if we took away 3 from that, negative 3 plus 3 is 0, and b times 0 is 0. So let's substitute that. We have 4 lots of 3 times negative 3. Then we're going to take away 2, and that's going to be equal to a lots of negative 3 take away 8. And the b bit is cancelled out to give us 0. Working this out, 3 times negative 3 is negative 9, take away 2 is 11, and multiply by 4 is negative 44. Right hand side, negative 3 take away 8 is negative 11, that's negative 11a. So divide through by negative 11, and a is equal to 4. So now when we go back to writing our fractions, let's write an answer. A is 4, so that would be 4 over x plus 3. And b is 8. So that would be 8 over x minus 8. So I'm just going to shade that in now to show it's our final answer. So it's highlighted in pink. This is our answer. Now, there's a few extra things here. So, for example, let's say that b was negative 8. What we would do is we wouldn't have plus negative 8 and negative 8 as a numerator. What you would do is have a minus 8. So you can bring the negative symbols on the numerator down to be the kind of symbol between the fractions. The other thing is this is a regular fraction. The numerator is smaller than the denominator, and by smaller, we're looking at the powers on the x. 12x, we've got x to the power of 1 there. Then with the x squared, that's x to the power of 2. Now, if that was the other way around, and you had a larger kind of value of x on top in terms of its power, if the power of x was larger on top, then what you would have to do is divide it to try and turn it into a mixed number. And the way you do that is algebraic long division. And if you divide the two things using algebraic long division, then you'll get a brand new fraction that you could turn in. We're going to plot first the line y is equal to negative 2x minus 3. So there's two key parts to this. The first part is the y-intercept. And the y-intercept is where the line is going to cross the y-axis. It's going to cross at negative 3. So it's a full coordinate of 0, negative 3. It's got 0 as the x-coordinate, because when we cross over the y-axis, that's where x is equal to 0. The second important feature is the gradient, which in this case is negative 2. So with the gradient is a change in y over the change in x. Now, if it's a whole number, we need to write this as a fraction, multiply y over x. So how do you do a whole number? Well, you can write whole numbers as fractions. You just write them over 1. So what we're saying is every time the y-coordinate changes by negative 2, the x-coordinate will change by 1. So if we go down on the y-coordinates and across one of the x-coordinates, the place that I just highlighted in pink there, we've gone down by 2 for the y direction and across by 1 on the x direction. And we just keep repeating that pattern over and over again And also do it in the other direction. This will be the opposite. This is going up 2 and then going across -1. And we get a line like this. Now, I'm just going to sketch this line. You should be using a ruler and a pencil. I just want to show you to join up all the points. So what we have here is the line y is equal to -2x minus 3. Now, something else I want to look at here. What if we're not plotting that at all? What if we're plotting the modulus of -2x minus 3? And for the modulus, we have these, they're almost like brackets, but they're just kind of straight lines at either side. So what does this mean? Now, with the modulus, that means that we can only have positive values. So let's write some notes on that. The modulus is with the lines at either side, so it means positive only. And when we're saying positive, what we want actually is positive y values first. So when we look at our line, you'll notice that the first part on the left-hand side, all of this is positive already. All the y coordinates are positive. The x coordinates are negative, so it's only the y coordinates that we're worried about with them being positive. Now, we've done the positive side, it then becomes negative. And what we're saying is the modulus only has positive y values. So when we go down to the next coordinate we've got plotted here, which is -1, -1, what we actually want to put is -1, +1. So the y coordinate is now positive. With the y-intercept, which was 0, -3, now it'll be 0, +3. The next one along that I plotted was 1 on the x-axis and -5 on the y-axis. So 1, -5 becomes 1, 5. And you'll see the same kind of gradient pattern here, but it's going in the opposite direction. And so then when you're plotting the modulus, you kind of plot this section here and join it up. And then this is the line, y is equal to the modulus of 2x minus 3. Now, the effect of the modulus is that you can probably see it's kind of almost like the lines bouncing off the x-axis. So with our original line, it will go straight through the x-axis, but with the modulus, it's now bouncing off. So that's something to be aware of, being asked to find a modulus of something. The next thing that we're going to look at is we're going to look at solving equations using a graph. So we're going to solve 3x plus 8 is equal to -7x take away 2. And we can solve this using the graph. Now, the way we do this is firstly have a look at the left-hand side. We've got 3x plus 8. We are going to draw the line y is equal to 3x plus 8. Then we look at the right-hand side, and we've got -7x take away 2. So we're going to draw that. Y is equal to -7x minus 2. Now, the green and the pink part are both equal to each other in our original equation, so we can make them both equal to y. They're still equal to each other. So let's plot the two lines. So 3x plus 8, the y-intercept is at 8, and the gradient, difference in y over x, is going to be 3 over 1. So when we go up 3, we're going to go across 1. But that's going to go off the graph, actually. So we need to go in the opposite direction. We go down by 3, we're going to go across by 1. And so we can plot the graph like this. Then we can draw a straight line through. So there's our first line. Now look at our second line, -7x take away 2. So the y-intercept is at -2. And the gradient is going to be -7 over 1. So we go down by 7 on the y-axis. We're going to go across by 1 on the x-axis. Now we're going to go down once, as you can see, before we run off the edge. So let's go in the opposite direction. We're going to go up 7, and I'm going to end up like that. And I can't really plot the next one. Now, the important thing here is I can just plot the little line segment I've got. I can estimate where it's going to carry on to. If you use a ruler, then you're going to get a really accurate line. The important thing about these two lines is you can see that they both cross over each other. They both intersect. So we want to look at the point of intersection. Now, the x-coordinate is -1. And the y-coordinate is at 5. And this is actually the solution to our equation, because we've got an x and a y coordinate, and we're looking for x's, and x is -1. So that's our answer. X is equal to -1. So rather than doing this algebraically, you can do it on a graph just by plotting the left and right-hand side separately, making them both equal to y, and the place where the lines cross over is your answer. Next, we're going to plot quadratic lines. So our first one is going to be y is equal to x squared plus x minus 2. Now, the usual method to plot things like this is to substitute. So if you choose a coordinate and substitute in, you're going to get some values you can use. So let's say that x is equal to 3. When x is equal to 3, that's going to give us 3 squared plus 3 minus 2, which altogether is going to be 9 plus 3 minus 2, which would be 10. And what you just found there is the y coordinate. So when x is 3, we'd have the coordinate 3, 10. And we can plot that on the graph. Now we can do that for every single value of x, but this is going to take a while. So let's look at a few shortcuts. The first shortcut is that the number on the end of this, the -2, that's the y-intercept, just like with the straight lines. So we know that our curve is going to go through -2. Now, the y-intercept is when x is equal to 0. So this means we don't need to substitute in x for 0. We can also factorise this. Now, I'm not going to go through it to factorise. We've got a revision slide on that. When you factorise this, you're going to get x plus 2 and x minus 1. Now, if we solve this for being equal to 0, we're going to get that x is equal to -2 and x is equal to a positive 1. And so it's the opposite sign, because what we're trying to achieve here is get one of the brackets to equal 0. So we multiply by 0 and get the answer 0, so it's equal to 0. So by solving the quadratic, we know the x-intercepts. We know we're going to go through x is 1 and x is -2. So I've got 2 more coordinates, again, without having to do any substitution. Now, once you've got these, you can then have a think about, well, what else do I need to substitute? So we can see we've got -2, 0, 1, 3. We don't have 2. So it might be you might want to substitute 2 in and see what that gives us. So 2 squared plus 2 minus 2. That's going to give us 4. So that'll be the coordinate 2, 4. And we can plot 2, 4. So it's almost like we don't really want to substitute for every single value. So we can use the x and y intercepts to give us an idea of which one to substitute. Because then after x is 3, if we substitute x equal to 4, it's going to go off the graph and it'll be a value that we can't use. So we don't want to substitute in anything larger than those. There's one more thing that's useful, and this is by differentiating this, we can find the turning point of the curve. So to differentiate, dy by dx, we bring down the power, so x squared becomes 2x. And then when you bring down the power, you reduce it by 1. So power 2 becomes power 1. X is to the power of 1, so you bring down the 1. And then if it's power 1, it's going to go into power 0 and disappear. And then the -2 doesn't have any power, so we're going to ignore that. It's basically power 0, and you multiply it by 0, it's going to go away. So dy by dx is 2x plus 1. Well, those just help us. Well, that's the gradient of the curve. So when that equals 0, that's when the curve has a straight gradient, which is going to be the turning point. So we say that 2x plus 1 is equal to 0 for the turning point. That means we've got 2x is equal to -1, and so x is equal to a -1/2. That gives us the coordinate for the turning point. Well, we know that x is going to be -0.5. You'll see we don't have the y coordinate for that, so we have to substitute it in. So that would give us -1/2 squared plus -1/2 take away 2. So -1/2 squared is going to give us 1/4. A quarter plus a -1/2, so plus negative, it's going to calculate to be a negative, a take away. So we're going to have a quarter take away 1/2, which will give us a -1/4, and then we take away 2. So it's going to be -2 1/4 altogether. That gives us the coordinate, -1/2, -2 1/4. And that's going to be the turning point of the curve. So with that, a little tricky to find, roughly here, we can see the turning point actually is not too far below the y-intercept for this one. Now, you'll notice there are some missing coordinates, and the trick here is that these graphs are symmetrical. So, for example, on the opposite side of the turning point, it's going to come up to the same height as the y-intercept. Then we've got the x-intercept, which we both have. And then on the right-hand side, after the x-intercept, it goes up by 4. So on the left-hand side, it's also going to go up by 4. It's going to be at the same height as the green coordinate. Then we go up to the top. When you go one to the left, it's going to be at the same height as the next coordinate. So you can use the symmetry of the curve to fill in the missing coordinates. And now we can sketch it. And don't do straight lines here. Try and make it curved. You don't have to draw it freehand. Make sure it goes through all the points. And there's the curve. So let's review the techniques that we used. We could find the y-intercept just by inspecting the formula. We could find the x-intercept by factorising and solving it for 0. We could find the turning point by differentiating it. And then we could find other coordinates that we wanted by using substitution. I only need to use 2 extra substitutions, although the differentiation also requires a substitution to find the y coordinate of the turning point. So that's how we plot a quadratic. Let's have a look at another example. So we have y is equal to -x squared plus 3x. So again, we can find some things about this without doing any substitution. We can look at the plus number at the end, and this one doesn't have a number added on at the end. That means the y-intercept is going to be at 0. Then we can factorise this to find the x-intercepts. Now, if you factorise this, we're going to take x out as a factor. That's going to give us, we'll take the negative out as a factor as well. So you take negative x out of negative x squared, you're left with x. And if you take negative x out of 3x, that's going to give you negative 3. And if you solve that equal to 0, that means in the bracket x would have to be equal to 3. And outside the bracket, x would have to be equal to 0. So the x-intercepts are at 0 and at positive 3. It's interesting for this one that if you don't have that kind of number at the end and the y-intercept's 0, it can be the case that the x and the y-intercepts are going to be the same. In fact, they will be. One of them will have to be 0. Next, we can differentiate this for the turning point. So dy by dx is going to be, bring the 2 down, negative 2, x to the power 1, reduce the power, and it's going to be plus 3. And what we want is for that to equal 0 for the turning point. So we can take 3 away for both sides and divide both sides by negative 2. So x is going to be equal to 3 over 2. It's going to be equal to 1.5. So now we can substitute in 1.5 for the y coordinate. So we want negative 1.5 squared plus 3 lots of 1.5. So you can write 3 over 2, or you can write 1 and 1/2. It doesn't matter which way you write it. So now we can substitute. So we have the 1.5, so we're going to square it. I want the negative version of that. So it could be negative 2.25. Then we're adding on 3 lots of 1.5, which is going to give us 2.25 or 2 1/4. The really important thing here is this is a negative 1/2 at the start. Don't square negative 1/2. Square the number you are substituting in, which is the 1.5, the 1.5, and then pop the negative symbol in afterwards. Remember, you do indices first, then you do subtractions. So this will give us the coordinate, 1.5, 2 1/4, which we can plot. So that's the turning point of the curve. Now, we need some more information to plot the bottom part of this graph. So what we're going to need to do now is do some more substitutions. Now, given that we've got values for 0, 1.5, and 3, it might be useful to look at 4. Now, I've run out of space to write this on the page, but we're going to do 4 squared, which is 16. I want the negative of that to negative 16. Then we're going to add on 3 lots of 4. That's going to give us negative 4 altogether. So that's going to be the coordinate 4, negative 4. Now, with the symmetry, we also know that negative 1 is also going to be down at negative 4. It's going to be at the same height. We might want to try 5 as well. So we want 5 squared is 25, so negative 25 plus 3 lots of 5, and that gives us negative 10. So we go 5 across, we go 10 down. And again, negative 2 from the symmetry will be there as well. So substituting just like I did with the 1.5 and just like I did for the 2 and the 3 in the previous question. So now we can draw the graph because I don't need any more substitution. I can see that negative 2 in 5 have got me right down to the bottom. So any of the substitutions will be a waste of time. And so there's a final answer. Next, we're going to plot a cubic. We're going to plot y is equal to x cubed minus 3x squared minus x plus 3. So again, we can inspect this to find some information. So we have a plus 3 at the end. That must be the y-intercept going through 3. So the y-intercept is going to be 0, 3. Again, the y-intercept's always got an x-coordinate of 0. Again, like the quadratics, factorising this is going to give us some points to look at as well. So if we take a full cubic, again, I'm not going to go through factorising a cubic because we've got a revision slide on that. So I'm just going to give the answer to it. But remember, some algebraic long division for this is going to be helpful. So the factorisation is going to be x plus 1, x minus 1, and x minus 3. Again, that factorisation will take you a bit of time, and that'll be worth, a couple of marks on its own. Now, if we solve it equal to 0, we're going to get the x-intercepts. And to make this equal to 0, one of the brackets has to be 0. So either the first bracket could be negative 1, because negative 1 plus 1 is 0. The second bracket could be positive 1, and the third bracket could be a positive 3. So they are our x-intercepts. We have negative 1, positive 1, and positive 3. Now we've got these pieces of information about what the turning points of the curves, and this is going to be done by differentiation. So again, if we start off with a full cubic, we differentiate it, bring down the power, and reduce the power by 1. You're going to bring down the power, and there's a number order there, so you multiply, 2 times 3 is 6, and reduce the power by 1, and you should get this. Now, at the turning point, this is going to equal 0, because that's where the gradient is flat. There's no steepness at a turning point. Now, if we factorise this quadratic, we're going to get our turning points. Now, again, we've got a different slide for revising factorising. I think this one's going to use a quadratic formula. And so what it's going to give you is x is equal to 2.2 and negative 0.2 to 1 decimal place. So we know the location of the turning points, but we only have the x coordinates. We want the y coordinates. So to get the y coordinates, we're going to substitute those into our original equation. So we're going to do 2.2 cubed, take away 3 lots of 2.2 squared, take away 2.2, and then add 3. And so for the y coordinate, that's going to give us negative 3.1 to 1 decimal place for the first one. Then do the same with the second one. We've got negative 0.2. We're going to cube it. We're going to take away 3 lots of negative 0.2. We're going to take away negative 0.2. That'll be a double negative, so we add on 0.2. And then we're going to add on 3. And that gives us 3.1 to 1 decimal place. So now we can plot the turning points. The first turning point, x, is going to be 2.2, and y is going to be negative 3.1. And you can't plot it exactly with the kind of level of detail on this, so just do it the best you can. The second turning point, x is negative 0.2, and y is a positive 3.1. And actually, it's really, really close to the y-intercept. So what we can do now is we can kind of plot the inside part of this curve like this. What we need to do now is just to see how this goes off the graph. So we're going to do some more substitution. So I'm not going to write this down, but I'm basically, I've got a point for 1, and then I've got just over 2, and I've got 3. So let's have a look at 4. So we'll have 4 cubed, take away 3 lots of 4 squared, take away 4, and plus 3. And that gives us 15. So what this tells us is this is going to go off this graph really, really quickly, actually. It's going to be something like this. It's not actually going to make x equals 4 before it goes off. At the top is going to be at y equals 10. When I get to 15, we're going to be about 2/3 of the way across there. Let's look at negative 2. So we want negative 2 cubes, take away 3 lots of negative 2, take away negative 2, double negatives, we're adding 2, and then we're going to add 3, and that gives us negative 15. It's going to be the same thing in the other direction. By the time we get to 10, we're going to be at 2/3 of the way across to negative 2, because when we get to 15, we're going to be the whole way across. And so there's our cubic plotted pretty accurately, I think, actually. So let's look at all the different techniques. Look at the y-intercept for the number at the end of your equation. You get the x-intercept by factorising the cubic. So you might be, doing a bit of trial and error here, testing and substituting 1, will it give us 0? You might be using algebraic long division. And then we use differentiation to find the turning points. Once you've got those, then what you might want to do is just try and substitute in a couple of extra points to get the full picture of what you're missing. Inequalities can be solved on a graph, and there's some really good advantages to it, which we'll see in a moment. So the first one we'll look at is y is greater than negative 2x minus 7, and y is greater than or equal to 7x plus 2. So what you want to do is to plot the two lines. So let's start with the top line. It's got a y-intercept at negative 7, so we can plot that. And the gradient is negative 2. So it's going to go down by 2 each time we go across one on the x-axis. And then in the opposite direction, it's going to go up by 2. And we can draw the line. Now you'll notice I'm going to draw a dashed line for this. And the reason is this is a greater than line. So we do a dashed line. If it's greater than or equal to, you do a solid line. And we'll talk about the importance of this in a moment once we've got both lines. Our second line is y is greater than 7x plus 2. So we have our y-intercept at plus 2, and our gradient is 7. It's going to go up by 7 each time. In the opposite direction, it will go down by 7 each time. And so we're going to have something a little bit like this. Now, you'll notice with this one, I'm doing a bold line, a solid line. This is because it's greater than or equal to, so you've got the equal sign involved, then that's where you have your solid line. Now, the benefit of this is that we're not looking at the point of intersection here. That would be solving the equation if these were equal to each other, and we have no equal signs. So we're looking at areas for our answer. So let's look at the first, y is greater than negative 2x minus 7. That means we want things that are greater than the line. We want things that are above the line. And you can see in blue, I'm just highlighting above the green line. For the pink line, that's also greater than. So we want things above the pink line. So we'll highlight that. And what we want is we want to shade in the part of the graph that I coloured in twice. And that's the bit at the top. You can see that's part of the green area and it's part of the pink area. So let's completely shade that in. Now the bits shaded towards the bottom on the left-hand side, that was only above the pink line. On the right-hand side, it was only above the green line. So we don't want those. So we'll rub out the extra shading that I had for working out. And so the shaded blue area is my answer. That's where both of these inequalities are true. Now, what you can do now is you can choose coordinates with that area, and they'll satisfy both lines. So let's say we choose the coordinate here, which is -2, 4. So if you substituted in -2 and 4, what you'll find is, substituting in -2 for x, you'll always be greater than 4. That's what it means. And so you can have any coordinate in here as your answer. But you will often be asked for, exactly any coordinate. Now, what about the dotted line and the thick line? Now, with the thick line, you're allowed to have coordinates that are on the line. With the green line, you are not allowed coordinates on the line. So when it's greater than or equal to, you're allowed coordinates on the line. Any coordinate on the pink line is fine. If it's just greater than, then you're not allowed any of the coordinates directly on top of the line. So that's something really important to take into account. Let's have a look at another inequality. So this time we're going to look at y is greater than -x squared plus 2x plus 2. And we're going to look at y is less than 2. Plot the two lines. So y is less than 2. Plot y is equal to 2, but it's going to be a dashed line because it's not equal when you read it out. It's just less than. It's not less than or equal to. So we're not allowed any of the coordinates actually on that line. It's only ones below the line. Then we're going to plot the quadratic. So use all the things that we revised for plotting quadratics. I'm not going to go through it in too much detail. So we know it's going to go through 2 on the y-axis. We know that if we factorize it, we're going to get the x-intercepts. And I'm not going to go through factorizing, but I believe it's going to be at -1 and 2. And you can, plot the quadratic, you can use substitutions and get accurate coordinates. Now, I'm not going to plot this too accurately. I just want you to get the idea of what we're doing. And it's greater than, so it's going to be, again, a dashed line. So it's going to be something like this. So then we solve this inequality. Again, make sure you put the proper effort into sketching it. You want to find more coordinates than I did there. But y is less than 2. So we want everything below the pink line. And y is greater than the quadratic. So we want everything that is above the green line. And I want to shade in the area that's shaded in twice. Now, the bit in the middle, that's only been shaded in once. So let's rub that out. The bit on top, that's only above the green line, so we can shade that out. Now, the bit on the left and right sides, that's not only below the pink line, but it's also above the green line. So we can have the entire area on the left. And then it's actually the same thing on the right as well. So all of the bit on the right is below the pink line, is less than, but it's above the green line. It's more than that. And so we can shade in the entire right side as well, as long as it's below the pink line. And so for this question, we've actually got 2 shaded areas. And that's something that can happen with quadratics, but not all the time. Sometimes you might have the bit in the middle or the bit on top. So you have different options, but this is an outcome you get sometimes with quadratics. We can also solve inequalities algebraically. So a basic example would be something that looks like an equation to solve. So let's say 2 lots of 8x minus 6 is greater than or equal to 68. Just pretend you solve an equation, but you keep the sign as it is rather than having an equal sign. So you can divide through by 2, giving you 8x minus 6 is greater than or equal to 34. You can add 6 to both sides, giving 8x is greater than or equal to 40. And then you can divide both sides by 8, saying that x is greater than or equal to 5. So you just solve it like you would any normal equation, you just have a different symbol. Now, where this changes a little bit is when we have quadratics involved. So let's have a look at x squared plus 2x minus 8 is greater than 0. Now, if we pretended this was equal to 0, we could factorize this quadratic. And so we factorize it. X times x is x squared. To get the -8, we need probably 2 and -4. And does that give us a positive 2? So -4 plus 2 would give us a -2. So actually we need a positive 4 and a -2. And then a positive 4 take away 2 gives us a 2x. And -2 times 4 gives us -8. If we solved it equal to 0, we would have x is equal to 2 and x is equal to -4. However, we don't have it equal to 0. It's greater than 0. Now you might think, well, okay, we can just put in the greater than symbol. X is greater than 2 and x is greater than -4. What happens here is that the greater than 2 is redundant, because anything that's greater than 2 is also greater than -4. So it's just a little bit of a clue that something's going wrong here. Now, the key to this, even though we're solving it algebraically, is we are going to need a little bit of a graph to show this. So we're going to draw our curve. Now, I'm not going to draw it accurately. Now, I know that the y-intercept will be at -8. I know the x-intercepts are at 2 and -4. And this is pretty much all the information we need, really. So I'm going to sketch a curve. Not worry too much how accurate it is. You'll see why in a moment. So it's going to be something like this. And we're saying it's greater than 0. So we also want y equals 0 in here as well. Now, just like when we're solving these graphically, we're going to do the same thing. So we want greater than 0. So we're going to shade in the parts of the curve that are greater than 0. And the parts that are greater than 0 are these bits here. This is the part of the curve that's more than 0. And so we're going to look at this in more detail. So the first bit that's greater than 0 is happening at -2. And the second bit that's greater than 0 is happening to be -4. Now, just look at where the graph's going. We're going below -4. We're going towards -5. So that means that x is going to be less than the -4, because answers less than that are on the line. On the other side, we see the 2. We can see our lines going towards 3. That's going to be things that are greater than 2. And so we have two different answers with different symbols, different arrows pointing in different directions. X can be greater than 2, that's above 0, or x could be less than -4, because then the graph is also going to be above 0 in terms of the y coordinates. So again, we've got two answers because we've got two separate parts of the graph shaded in. Now let's have a look at another example. So we're going to have a look at -x² plus 7x is greater than or equal to 0. So again, we want to sketch the quadratic. Now, there's no plus number at the end, so it's going to be 0 for the y-intercept. If we factorise this, we're going to get something like this. So if we pretend that it's equal to 0, x would equal 0, and x would equal a positive 7. So we know that 7 is going to be an x-coordinate as well. Now, if we sketch this graph, it's going to look something like this. And again, I'm not too concerned how accurate this is. I don't know how high it's going to go, actually. But it's going to be something like this. And we want when it's greater than or equal to 0. So which part of the curve is above 0 for the y-axis? So shade it in. It's the kind of loop in the middle. Now let's have a look at the numbers. So we've got when x is 0 and we've got when x is 7. So you can see that we're allowed values in between 0 and 7. So then when we're writing this down, we don't want x equals 0 and x equals 7. We want x is going to be greater than 0 and x is going to be less than 7. And then because the original is greater than or equal to, we can pop the equal signs on those as well. Another thing we can do is we'll write that in an alternate form. So x is greater than or equal to 0 and x is less than or equal to 7. They can be combined into 0 is less than or equal to x, and x is less than or equal to 7. So both of these are the same thing. They represent the same information, but you can just combine them together so you're writing down less x's, less to write, basically. Now have a really careful look at our two examples here. So the one we've just done, above 0 on the y-axis, you can see we've got the kind of curve, and it's all in one piece. In our first example, we can see when y is above 0, that we have two separate pieces. So that's just a clue to how to write it. Two separate pieces, you want two separate answers, like x is greater than 2 and x is less than -4. If the whole thing's together, then that's a clue you want it all combined. So you want 0 is less than or equal to x, which is less than or equal to 7. Looking at transformations of functions, we've got the black line on each graph, and this is the line f of x. So we don't actually know what the formula of this line is. Now the quadratics is going to be x². We don't know exactly what form that's going to take. So each one is y is equal to f of x. So let's have a look at ways we can transform this. So on the first graph, in blue, we're going to do y is equal to f of x plus 2. And so if we do that, what's going to happen is the graph's going to shift 2 places on the x-axis because 2 is next to the x. And so if you just take important coordinates, so for example the x-intercepts, these are going to shift 2 places across. And so the base of this graph, the curve, is going to be here. And then where it goes off the graph up the top, that's going to shift across 2 places. So roughly you're looking at a graph like this. Now you might think, well, this has gone backwards by 2. It's not gone forwards by 2. And so you're always going to think when you're transforming functions, it's going to do the opposite of what you think. You're almost saying if you're adding x to 2, you want x to appear 2 places sooner. If you take x to be, say, time, and from left to right, you're going forward through time. So you've added 2, it's appearing 2 blocks sooner. And so what we can say about this is you look at the coordinates, each coordinate has gone down by 2, and the y coordinate has stayed the same. Let's have a look at another transformation. So let's have a look at y is equal to f of x plus 2. Now this time the plus 2 is on the outside of the brackets. So in effect you can rearrange this, and if you take 2 away from both sides, we've got y take away 2 is equal to f of x. And so we can see that rather than the last one where the x had something added to it, this time the y is having something added to it. And you're going to do the opposite of what you think. So if y is minus 2, you're actually going to add 2. So again, take important coordinates, like for example the x-intercepts. They are going to go up by 2 for a new graph. When we go off the graph, that'll go up by 2. Now that's going off the graph, so it might not be the most helpful to look at those. You can look at the y-intercept. That's going to go up by 2 as well. You can see the y-intercept is 1 across from the x-intercept, so it's going to be 1 across in the other direction as well. So now we can do a little bit of a sketch of this line. So it's going to look something like this. So the whole thing has shifted up 2 places. Now again, if you look at the coordinates, what's happening to the coordinates is the x-coordinates are staying the same, but the y-coordinates, you're adding 2 to them. So what we have here is these are basically translations. So we have translation on the x-axis, when you have your number inside the brackets with the x, and then we have translations on the y-axis, with the numbers outside the brackets, and if you rearrange it, you can see it'll be next to the y. So let's have a look at some more transformations. So let's move on to the second graph, because I don't want to write too many on the same graph because it's going to get confusing. So our next transformation is going to be y is equal to f of 2x. So we think about what's going to happen with the coordinates here. It's on the inside of the brackets, the numbers next to the x, so we're going to have something happening to the x coordinates. It was the opposite of what we expect. So this one's being multiplied by 2. So the opposite of that is going to be divided by 2. So the x coordinates are going to be divided by 2, and the y coordinates will stay the same. So again, find some important coordinates. So again, we've got the x-intercepts. One of them is at -1. So divided by 2, it'll be at -half. One of them's at -3, divide that by 2, and it's going to be -1.5. So we know the curve is going to be here. The y-intercept is when x is at 0, so that's not going to change. If you divide 0 by 2, you still get 0. Again, we can use a symmetry to have the point on the other side as well. So what about where the graph goes off the end of the page? Well, one's just after 1, so that'll be half of it just after 0.5. And then the other one is at just over -5. So divide that by 2, just over -2.5, and then we can draw that. And so what you can see is, if you divide the x-coordinates by 2, you actually make the curve kind of more squashed together. It takes up half as much space on the x-axis. Let's have a look at another. So we're going to look at y is equal to 2 lots of f of x. Now again, with this we can rearrange it to get that number onto the y. So that would be y is equal half of y is equal to f of x. So it's divided by 2. Now, as usual, it does the opposite of what you'd expect. So if you're dividing the y coordinate by 2 in the equation, in our answer, we're going to be multiplying it by 2. So this will be y times 2. So we multiply all the y coordinates by 2. Now, the x-intercept is really important here because that's when y is 0. If you multiply 0 by 2, you still get 0. That's not going to change places. What will change is where it goes off the page. Now that's where y is 10, so that's going to end up at y is 20. Well, we can't plot that. But if we look at when y is 5, when we double that, we'll get 10, which is where it goes off the page. Now, all you have to do is look at the 2 places where y is equal to 5. If you double it to 10, you just draw the same coordinate at the same place on the x-axis, but then move up to 10 on the y-axis. And we can actually probably draw this now. Perhaps one more important point is the turning point of the curve, which is that when y is equal to 1. So if you double it, it'll be at y is equal to 2. And so the curve is going to look like this. And so what you can see here is that our curve, again, it looks like it's kind of squashed together, it's got smaller. What's actually happened is it has got a lot bigger. You can see in the negative part of the graph at the bottom, twice as big in the lower half. It's also twice as big in the upper half. It's just that you can't see the top half of it because it's gone off the page. Now, this is more equivalent to enlargement. We're kind of stretching and squashing the curve, making it bigger and smaller. So it is effectively a kind of enlargement. But you might be better off calling it a stretch. Whereas the translation, you kind of moved the curve around. The next one we're going to look at is y is equal to f of negative x. Now, the negative symbol on the x, so all this means is that the x coordinates are going to become negative versions of themselves. So if you look at the x-intercepts, x is 3 and negative 1. They're going to become negative versions of negative 1, negative 1 will be positive 1, and negative 3, negative 3 will be positive 3. And so the bottom of our curve is now going to be on the other side. The y-intercept is really important because that's x is 0. Negative 0 and 0 are the same thing. That's not going to change it. We can use symmetry to see on the other side that's going to be that height. And then perhaps we'll look at where it goes off the graph. So we're going off the graph at 1 and negative 5. So that's going to become negative 1 and positive 5. So a curve is going to look like this. You'll notice it looks exactly the same. It's just on the other side of the graph. And effectively, this is a reflection in the y-axis. So these are reflections. And it's a bit odd that, if it's a y-axis reflection, y is the line of symmetry, the mirror line, then it's the x coordinates that become negative, y stays the same. Next one to look at is y is equal to negative f of x. And again, if we rearrange this, we can put the negative on the y by multiplying both sides by negative 1. So what this means is that the y coordinates are going to become negative. And logically, I guess this is going to be an x-axis reflection. Now again, you can look at the coordinates. So the y coordinates being negative, the x-intercepts where y is equal to 0 is really important because they're going to stay the same. But then the turning point at negative 1, the negative version of that, negative 1 is positive 1. So the turning point of the curve is going to be the other way around. The y-intercepts at 3, so that'll become negative 3. And then look at the place where it's going off the page at 1 and negative 5. They're going to stay the same, they're just going to be down at negative 10 instead. And so we've got a reflection in the x-axis and a reflection in the y-axis to look at. Now the last thing to look at is something that's interesting. It's called the modulus. So with the modulus, the first one we're going to look at is y equals f modulus of x. I'm using these lines to show the modulus symbol. What this means is that the x coordinates are going to be positive. So we're going to have a positive x and y is going to stay the same. So let's have a look at our graph. Where are the x coordinates positive? Well, the positive on the right hand side, which I'm highlighting in purple, this part is going to stay the same. Now we are going to plot some lines in the negative part of the x-axis, but rather than being the line you can see the rest of the curve, which is the negative x-axis values, what we're going to do on the negative side is plot the positive x-axis values again. And it's actually going to look like this. So all we've done on the negative x values, we've put in the y coordinates of the positive x values. Let's look at the version for y. That'd be y is equal to the modulus of f of x. Again, the line's showing it's positive. So when you look at the coordinates, x stays the same and y is going to become positive. So we look at the curve, and we look at the part of the curve where y is positive. So I'm going to highlight that in purple. And this is all part of our answer. It's going to overlap with the previous answer as well. Now, when we get to the bit of the curve where y is negative, we just make it be positive. So the turning point of the curve is negative 1. It has to be positive. Y coordinates have to be positive now. So it's going to go up to positive 1. And so it's going to look like this. So it's almost like you've kind of bounced off the x-axis when you're plotting the line. So there are the 4 transformations we look at. We've got translations, we've got enlargement, so stretches and squeezes, we've got reflections, and we've got the modulus. One final point with these is you might be asked to do a combination of these. So it might be that you get y is equal to negative f of 2x, and that means you're both going to do a kind of squash on the x-axis by a factor of 2, and then you're going to reflect it in the x-axis. So again, just be careful when you have combinations of these. You do both transformations to the x and y coordinates. We're going to look at different things we can do with a straight line, and for all these questions, we're going to use the same pair of coordinates. So we're going to look at everything we can do with the coordinates, -9, -6, and 3, 7. So what can we do with a line in between those two coordinates? First thing we can look at is the midpoint. For the midpoint of the line, what we need to do is we need to look at the x and the y coordinates and kind of look at where's in the middle of those coordinates. So the way to do it is for the x coordinates, add them together. Let's say we've got x1 and x2. So let's say our first set of brackets is x1 and y1. Our second set of brackets is x2 and y2. Add the x coordinates together and divide by 2. And then do the same thing with the y coordinates. That's going to give us -9 plus 3 divided by 2. And it's going to give us -6 plus 7 divided by 2. And so we work that out. -9 plus 3 is negative 6, and divide it by 2, we're going to get negative 3. Then we can do it with the y coordinates. Negative 6 plus 7 is going to give us 1, and then 1 divided by 2 is going to give us a half. So the midpoint, the coordinate in the middle of the line, is negative 3.5. Next, we'll look at the length of the line. To find the length of the line, we're going to use Pythagoras' theorem. So we need to know the kind of distance in x and y to make our triangle. The distance in x, we want the difference between x1 and x2, and then we're going to square that. So that'll be the first side of our triangle. Then we're going to add to that the difference between y1 and y2, and that'll be the second side of our triangle. And then we want to square root our answer to find the hypotenuse, which will be the length of the line. So that's going to be negative 9 take away 3, which will give us negative 12. Then we've got our y's, so we've got negative 6 take away 7, which will give us negative 13. And what the square root of the answer to that. So that's going to give us negative 12 squared is 144. Negative 13 squared is going to be 169. Altogether, that's 313. And the square root of 313 gives us 17.69 to 2 decimal places. So that's going to be the length of the line. Next, we can find the gradient of the line. The gradient is the change in y over the change in x. So we're going to look at our y coordinates. It's going to be similar to the Pythagoras theorem, actually. So it's going to be the y1 minus y2 and the x1 minus x2. And so altogether, that's going to give us negative 13 over negative 12. And then if we simplify that, they're both negative, we can make it positive. It's going to be 13/12 the gradient. Change it to a mixed number, 1 and 1/12. That's how steep the line is. Other things we can do with the gradient. We can have parallel gradients. So the gradient of parallel lines. Parallel lines are going to have the same gradient. So a parallel line will have the gradient 13/12, which again is 1/12. Perpendicular lines, these are lines that are at a right angle to this line. They're going to have a negative reciprocal gradient. And to do that, you make the gradient negative and you flip the fraction upside down. So 13/12 will become 12/13. And then we can't simplify that any further. The last thing we're going to do is we're going to find the equation of the line. Now, this is a technique you need to find the equation of all kinds of lines, given all kinds of different clues. To find the equation of the line, it's going to be y is equal to mx plus c for the equation of any line. So what we want is to substitute into this. Now, we know what the gradient is already. It's 1 and 1/12. And what we want to do is we want to put in x and y coordinates from this as well. Now, I can choose either of the two coordinates. I'm going to choose the x2, y2 because it's positive numbers. So y is 7, m is the gradient, which we had as 13/12 as a fraction, and x is 3 from our second coordinate. And so we can work this out to find out what c is. So first we can multiply 3 by 3, so that 7 is equal to 39/12 times that fraction by 3. So what we're going to do is take away 37/12 away from both sides. Now, if you do that on a calculator, what you're going to get is that c is equal to 3 3/4. So when we write down the equation of the line, it's going to be y is equal to, let's write the gradient as a mixed number this time, so 1 and 1/12, x plus 3 3/4. So these are all the different things you could be asked to find from a line. Note that with this, I'll start out with 2 coordinates, but you could start off with a coordinate and a gradient. It could give you a parallel gradient or a perpendicular gradient to start off. It could be all kinds of different starting points. But as you go through these things, you're going to be getting the right numbers. The equation of a circle tends to look like this. So we're going to have an x inside a bracket with a number, and that's squared. We're going to have a y inside a bracket with a number, and that's squared. That's going to be equal to a number at the end. So what can we take from this? Well, we know that the center of the circle is going to be the coordinate 3, -1. So the 3 and -1 are from the numbers inside the brackets. Just note the signs are being reversed. The radius is the square root of the number at the end. So the radius of that circle would be 5. So that's what you typically see for the equation of a circle. Now, there is an alternate form. You can have an equation of a circle that looks like this. X squared take away 2x plus y squared take away 12y minus 44 is equal to 0. And what we want to do really is change this into previous form. It's really easy to get the centre and radius from the previous form. The way we do it is completing the square. So we complete the square for x. So all we're doing is making this squared into a power 1, x, and then the coefficient on the x term is being reduced by half. If we do that though, we're not just going to get x squared minus 2x, we expand it, we're also going to get a positive 1 at the expansion from the negative 1 times negative 1. So we have to take away the extra positive. Then we complete the square for the y. Y squared becomes y, 12y will become 6. But again, negative 6 times negative 6 gives us 36. We need to take away the extra 36. So now we need to collect up all the number terms. So we have a negative 1, a negative 36, and a negative 44. So the bracket part looks right. Collect up all the terms. We're going to get negative 81, which is equal to 0. And we want to get that on the right-hand side. So we're going to add 81 to both sides. So when you add up all your numbers, reverse the sign and move it to the side. That means that now we can figure some things out about this. So we know that the centre is going to equal 1, 6. Again, the sign's been reversed. And the radius is going to be the square root of 81, which is 9. So that's how we use the equations of circles. One more thing you might be asked is to find the tangent to a circle. And a tangent is a line that just touches the circle at one edge. It's at a right angle to the radius or diameter. So as an example, we're going to find the tangent of the equation of a circle, and we're going to have a coordinate with it. Put the tangent at the point 3, 6. So 3, 6 is on the edge of the circle, and the tangent will touch the circle just at that point. So how do we do this? So the first thing is we want the gradient of the radius. The gradient can be changing y over x, and we actually do have 2 x coordinates and 2 y coordinates. So let's take the 3, 6 first. So we've got the y coordinate and the x coordinate of 3, 6. So where's our other coordinate? Well, we know the centre of the circle. It's going to be at 5, 3. So we can take away 5, 3 from this. And so this gives a change in y and x between the centre of the circle and the point at the edge where the tangent hits. So 6 take away 3 is 3. 3 take away 5 is negative 2. So that will give us negative 3 halves. Now we can find out the tangent gradient. The tangent gradient, because it's at a right angle, it's a perpendicular line. So it's going to be a negative reciprocal. So it's going to be negative x over y rather than y over x. So gradient's already negative, a double negative will be positive, and then we flip the fraction upside down. So the tangent gradient is going to be 2/3. So now we can find its equation. We want y is equal to mx plus c. We're going to substitute in values for y. It's got to be a point at the edge of the circle, so you can't use a centre here. So we have to use the 3, 6. So y is 6, x is 3. And now we know the gradient. The gradient is 2/3. So if we expand the bracket, that's going to give us 6 over 3, which is 2. So 6 is equal to 2 plus c. So take 2 away from both sides. C is going to be equal to 4. That means the equation of the tangent is going to be y is equal to 2/3 x plus 4. Last thing I want to do, let's just have a little visual of what a tangent looks like. So I'm going to sketch a rough circle here. So the tangent comes by the circle and it touches it at one point. And from the centre to that point on the edge, we have a radius. It's going to be at a right angle. So we have the tangent, we have the radius, and it's at a right angle. Parametric equations are an alternate way of writing down equations. So let's say we have x is equal to t minus 1 and y is equal to 2t squared. This is a parametric equation. Now, what does this mean? Well, we're going to go through the process of turning this into the kind of equation you're used to. And once we've done that, then we can look back and think about why this might be used. So what we want to do is we want to make both of these equations equal to t, so we can make them equal to each other and merge them. So for x, this is pretty simple. We can add 1 to both sides, and so we get t is equal to x plus 1. That's pretty simple. Now, moving on to the second one, let's do it in a different colour, so we can colour code. We have y is equal to 2t squared. So what we're going to do is we can divide both sides by 2. That will give us half of y is equal to t squared. And then we can square root both sides. So we're going to get the square root of a half y is equal to t. And now these are both equal to t, we'll make them equal to each other. So x plus 1 is equal to t, which is equal to the square root of a half y. And this doesn't look like an equation. Normally with line equations, we have y equals. So let's try and make y be the subject. So we can square both sides. That's going to give us x minus 1 all squared and a half y on the other side. Then we can multiply both sides by 2. and that's going to give us y is equal to 2 lots of x plus 1 squared. You might want to multiply at the brackets. So if you multiply at the brackets, you're going to get y is equal to, and remember to multiply it by 2 at the end as well, we're going to get 2x squared plus 4x plus 4. Now, the point of this is with substitution. So let's look at substitution. Let's say we know that y is equal to 1, or we want to find the x coordinate when y is equal to 1. So how do we do that? So with a parametric equation, we'll just say, well, if y is equal to 1, y is going to equal 2t squared, but we're saying that y is equal to 1. So we can solve this, we can divide both sides by 2 to get a half, and then we can square root it. So y is going to be the square root of a half. Then we can substitute that in for x. So we can say x is equal to the square root of a half minus 1. So very quickly, we're getting x and y coordinates out of this. Even better, we have this third variable, t, and it might stand for something like time. And if you have values for t, then your substitution is going to be even easier. Now let's have a look at y equals 1 with our formula at the bottom. So we can say 1 is equal to 2x squared plus 4x plus 4. So to get what x is going to be here, we're going to have to maybe rearrange this. Let's take 1 away from both sides to get 2x squared plus 4x. Then it'll be minus 3 equals 0. And then you want some kind of method to factorize this. You might have to use quadratic formula, for example, and that's going to take you a bit of time. And then once you do that, then you're going to get your value for x out. So hopefully what you can see here is a regular kind of equation for a line. It's very good at finding y coordinates. You can substitute x in and get a y coordinate in quite easy. If you're trying to find a x coordinate and substituting y, it's not very helpful. So again, it's just an alternate form to write it so you can do substitutions easier in some circumstances. Now, we're going to look at a harder version of this. So this was a quadratic. Let's look at a circle equation as a parametric. So we're going to have x is equal to sine theta plus 3, and we're going to have y is equal to cos theta plus 7. Let's make that minus 7 actually, so we can see how positives and negatives work. Now, the way we're going to combine these together is our third variable here is theta. And we can't really get rid of the sine and the cos to get theta on its own. What we can do is use a trigonometric identity. Sine squared theta plus cos squared theta is equal to 1. And so we can use this to combine the two terms together by make sine theta and cos theta the subjects. So we'll come back to that in a moment. Let's rearrange. So for x, we're going to take 3 away from both sides. That will leave us with sine theta is equal to x minus 3. With the cos, going to add 7 to both sides, so that'll be cos theta is equal to y plus 7. So then if we bring back our trigonometric identity, we want sine squared theta to substitute in. Now we have sine theta. Sine theta is x minus 3. So we want the sine squared theta, we just need to square it. Then with squared theta, we have cos theta, it's y plus 7. So all we need to do is square it. And now we've combined the two parametric equations together into a single form. And you might notice that's actually the equation of a circle. Now it came a bit of rearranging, but we've got it straight away. So now we can say things about the circle. We can say that the centre of the circle is at 3, negative 7. And we can say that the radius of this circle is the square root of 1, which is 1. And again, there's different benefits to both forms. You see, combined together, it's really easy to find the centre and the radius, whereas when they're a pair, it's going to be easier to substitute in values for theta, or even values for x and y and rearrange. But rearranging with a full equation is going to be much more of a mess. Before we look at binomial expansion, we have to look at Pascal's triangle. Now, the triangle has an infinite number of rows, but we are going to have a look at the first 8 rows. Now, it starts off with a 1. And for the next row, we're going to have 1 and 1. Now, it becomes clear what's happening with the next row. We have 1, 2, and 1. And what's happening with this triangle is that each number is the 2 numbers above it added together. So the 2 is the 2 ones above it added together. On the edge, you only have access to a 1 and a blank space, so they stay as 1. So for our next row, the edges of Pascal's triangle are going to be 1s, but then we have 1 plus 2 is 3, and 2 plus 1 is 3. And so we can generate the triangle like this, each time adding up the 2 numbers above. So 1 plus 3 is 4, 3 plus 3 is 6, and 3 plus 1 is 4. So let's continue. So again, each time, just add the numbers above. And you can see in alternate rows, you have two identical middle numbers. So if it's an even numbered kind of number of terms that you have, then the middle two numbers will be the same. If it's an odd number like this one, then the middle two terms will be different. So let's just generate the last few rows. You'll also see that this is symmetrical. So the numbers on the left are the same as the numbers on the right. Now, what this is used for is to find the patterns when you expand brackets. So let's say we had a quadratic. We had x plus 1 squared. If you expand this quadratic, you get x squared plus 2x plus 1. And compare that answer to the second row of Pascal's triangle. We've got a 1, a 2, and a 1 in the triangle. And then if you look at the coefficients here, we've got a 1 x squared, a 2x, and then a 1. So it's matching that pattern. So then when we look at x plus 1 cubed, that should give us x cubed plus 3x squared plus 3x plus 1. Again, using that pattern. And then we can do, well, if it's the power of 4, we can use this pattern. We're going to have x to the power of 4 plus 4x cubed plus 6x squared plus 4x plus 1. Now, as well as the coefficients on the x matching the rows of Pascal's triangle, so for example, on the fourth row, we've got 1, 4, 6, 4, 1. In our expansion, we've got 1, 4, 6, 4, 1. Also have a look at the powers. Now, the powers on x are going down each time. So we've got power 4, power 3, power 2, power 1, and then we don't have a power at the end, which means it's going to be a power 0. We can use this pattern to write a formula. So if you've got a plus b to a power, so like that's what we've just done. A would be x, b will be 1, then we've got the various powers. The formula is going to be n over k multiplied by a to the power of n minus k multiplied by b to the power of k. And what this does is this will generate the terms in the expansion. So let's say in the kind of power 4 expansion we just did, let's say we only wanted the term on x squared. What would we do? So what we would do, looking at this formula, is first we'd have n over k. Now what that is going to give us, n is the power, so this is a power 4 expansion, and k is going to be the power we're looking at. So we're looking for power 2. Then the a, that's going to be our first term, which is the x, so that's going to be x to the power of n minus k, so 4 minus 2. And then b, which is a 1 here, that's going to be power of k, which is going to be the power of 2. If we do this multiplication, we should get 6x squared. Now, the key thing here is, what is this bracket about? We've got kind of something that looks like a vector. We've got 4 over 2. Now, what that does is that generates the terms in Pascal's triangle. So if you've got n over k, this uses a formula where it takes the factorial of n, that's n, multiplied by all the numbers below it, all the whole numbers below it, and it's divided by k multiplied by n minus k. And it generates the part of the triangle you're looking for. Now, the n is the row, and k is the column. And remember, columns always start with 0. So we label this for the bottom row. We're going to have column 0, 1, 2, 3, 4, 5, 6, 7, and 8. But obviously that's going to be different for each row. Again, each row starts with 0, and then you just count your way along. So when we're saying 4, 2, we're saying we want the number in row 4 and column 2. So we look for row 4, then we look for column 2, so 0, 1, and 2. And we can see that's going to give us the 6. So the kind of vector here, the row and the column, that's going to give us 6. X to the power of 4 minus 2 is x to the power of 2. Then we multiply it by 1 squared, and 1 squared is 1, so 6 times 1 is going to give us 6. And so you can see by applying the formula, we've got the 6x squared straight away. So it's useful for finding particular terms. And you might be asked in the exam to find maybe the last 2 terms or the first 2 terms, for example, or perhaps a term on a particular power, like we just did here. The last thing to think about is that you don't need to draw the triangle out for every single question. So we're talking about the kind of vector notation here with the n and the k. There's actually a button for that on your calculator. And the button for it is the NCR button. So you type in n, there's then a button with NCR on it, and then you press K. When you type that into your calculator, you should see N, you should see a C, and then you should see the K. And again, that's just a method for your calculator to know which row and column of Pascal's triangle you want. Arithmetic progressions are similar to kind of basic sequences you find on GCSE. But you might have slightly different terminology. So you might say UN, which just means the nth term. So let's say the nth term is a half n plus a third. So you'd have to be able to generate the sequence. So to generate the sequence, n would start off with 1, your first term. So you'd have 1/2 plus a third. And if you work that out using your fraction skills, but a half plus a third is 5/6. Then for each part of the sequence, the way it's going to scale up is it's going to go up by 1/2 each time. So for the second part of the sequence, n will be 2. So that'll be 2 halves, which is the whole one, plus a third. That'd be 1 and 1/3. Then the next part of the sequence, n would be 3. So you have 3 halves plus a third. And what you might find here is rather than working in mixed numbers, it might be better to work in improper fractions. Now, a half is going to be the same as 3/6. So we just add on 3/6 each time. So 8/6 is the same as 1 1/3, but it's just easier now to be adding on the 3 to the numerator each time to generate the sequence. And then the sequence would carry on forever. You might be asked for specific parts of the sequence. So you might be asked for, say, U10 for the 10th part of the sequence. That's going to be a half times 10 plus 1/3. Now, if you did this with mixed numbers, a half times 10 would be 5, and 5 plus a third is going to be 5 and 1/3. If we can keep it consistent to what we're looking at before, then we could say, well, this is 16/3, which would be 32/6. So be flexible in the way you can write your fractions, depending on context. Because if you have the denominators all the same for all parts of the question, it's easier to compare. It's a lot easier to see that 32/6 is a lot larger than 17/6, the 5th term, than looking at 5 and 1/3, and then kind of having to guess how it relates to the other parts. If you are asked to generate the nth term from the sequence, then looking at this sequence, you should be able to see that it's going up by 3/6 each time, which is the same as adding on a half each time. And so if it does the same thing each time, and it does, then you know it's going to be a half n. So the number on the end, the coefficient on the end, is always what it's increasing by each time. Now, if that was true, it was a half n, the first term would be a half times 1, which is a half, and it's not, it's 5/6. So you think, well, what do we add onto a half to get the first term 5/6? Now, 5/6 and a half, the denominator is different. So think what a half is 3/6. How do you get from 3/6 to 5/6? We've got to add on 2/6, which is the same as a third. So that's where the third is coming from in this. So this is kind of recap how it works at GCSE. There's more complicated fractions involved, which is quite common. Now, another thing you might be asked to do is to add up a certain number of terms in the sequence. And we've got a formula for this. So we have this symbol. This is the sigma symbol. And the sigma symbol just means sum. It means we're going to add up all the things we'll look at here. Now, on top of this symbol, we have n. This is the number of terms we're going to add up. And then below the symbol, we've got a number. And the number underneath, that's where the adding up starts. Very often, it's going to be equal to 1. Next to this, you have the nth term. So we go for the previous question. We could have a half n plus a third. And this is the kind of terminology you'll see in the exam if it's asking for the sum. The formula for this is S is equal to n over 2 multiplied by 2a plus n minus 1 multiplied by d. And so we have to think about where all these different letters come from. So n is the number of terms to add. The a is the first term of the sequence. So we know from our previous work here that the first term is 5/6, but that's something you can generate from the nth term by saying that n is equal to 1. D is what we call the common difference. The common difference is what's changing each time. So in this sequence, it's going up by a half each time. So the common difference is a half. So let's say we were given a question on this. Let's say we said, right, we're going to sum up. We want the first 5 terms, the one that I just rotate here. I'm going to start off adding from the first term. Then in the brackets, you actually have the nth term. So we will substitute into the formula. S is equal to the first 5 terms divided by 2. 2 lots of the first term, A, so the first term is 5/6. 2 lots of 5/6 plus n minus 1, so 5 minus 1, multiplied by the common difference, D, which is a half. So we can start to work this out. So 5 divided by 2 is going to give us 2.5. 2 multiplied by 5/6 will be 10/6. We're going to add on to that. 5 take away 1 is 4, so 4 multiplied by a half. We can continue working through this. So we have 2.5 multiplied by 10/6 plus the half of 4 is 2. So if you do 10/6 plus 2, and then multiply it by 2.5, the answer that I'm getting is 6.16 recurring, which we can write as a fraction. 1.6 recurring is a sixth, so it'll be 9 and 1/6. So if you want to spend some time on this, you can continue working out with fractions, or you can do what I just did there and just work it on a calculator as a decimal and then convert it back into a fraction at the end. You're probably better off keeping it in fractions the entire way with your working, but I'm just going to speed this up because it's just a revision slide. So now what I've done here is I've added up the first 5 terms. Now we have to have these written out, so let's see if this actually works. So 5/6 plus 8/6 plus 11/6 plus 14/6 plus 17/6 should give us 9.16 recurring, and on my calculator it does. So we can see that the formula should work. One last detail is that for this formula we have k equals 1. The starting point of where we are adding from is the first term. Now if the starting point isn't 1, let's say it's 2, then you have to take the first term off your answer, because this formula doesn't take the first term, the kind of starting point, into account. If you have to start counting at the third term, then you do your formula. That'll be the answer for all the terms up to where you're looking for, n. And then if you want to start counting at the third term, you have to take away the first and second terms. So just be aware of your starting point if you need to take anything away. If k was quite large, let's say k was equal to 5, you could actually use the formula to find the sum of the first 4 terms and use any as 4. And then you would take that away from your answer, which has all the terms added together up to wherever your endpoint was. Geometric progressions, again, you might see some notation for the nth term. You might have un is equal to, and let's say, for an example, you could have 2 times 3 to the power of n. So this is going to describe a sequence. In the first term of the sequence, n will be 1, so that would be 2 times 3 to the power of 1. Well, power 1 doesn't change the number, so 2 times 3 is 6. When n is 2, this would be 2 times 3 to the power of 2, which is 2 times 9, which will give us 18. Then we'd have 2 times 3 to the power of 3, which is 54. Then we'd have to the power of 4, 162, and the power of 5, which is 486. See, these numbers are starting to get bigger quite quickly. As usual for a sequence, the number of numbers in the sequence can go on infinitely, unless you be given a limit for the sequence. Now, what's happening in this sequence each time we are multiplying by 3. So this is a times 3 sequence. So geometric progressions are about sequences where you multiply or divide. Arithmetic sequences are sequences where you add or subtract each time. And each one uses different formulas. Now for this one, if you can see it's times by 3 each time, you write 3n. That's where that comes from. Then you think, well, if for the first term 3n would be 3 to the power of 1, which is 3, how do I get to the 6? And so that's where we have to then add on the multiplying by 2 to get to our first term. You might be asked for specific terms. Let's say u10 will be the 10th term. So you do 2 times 3 to the power of 10. So we're going to take my calculator, 3 to the power of 10 multiplied by 2 is going to give 118,098. So again, when you're doing these kind of sequences, they get very, very large very quickly. Now, again, there's some special notation to look at. So we've got the sigma symbol for the sum. And on top tells us how many parts of these we want to add together. And the k underneath will tell us the starting point. Commonly, you'll see k being equal to 1. After this, you'd have the nth term. So you would have whatever you're multiplying by, you have the thing you're multiplying, and you would have the power. The formula for the sum is the sum of the first n terms is a multiplied by 1 minus r to the power of n divided by 1 minus r. We need to know what all the different letters mean. So n is the number of terms to add. A is the first term. In this case, it's 6 for our previous example. R is what we call the common ratio. This is basically what you're doing to the sequence each time. So in our last example, we're multiplying by 3 each time. So the common difference would be 3. It's the same as the number in the nth term that's to the power. Last thing to look at is what we've got the k. This is just the starting point of where you add. So we're going to start at the first term usually and have k equals 1. We'll talk about other numbers later. So let's try adding up the first 5 terms of our original example. Now we can actually do it because we've got the first 5 written out, but what we're going to do is just test if the formula works. So the sum of the first 5 terms, the first term is 6, we're multiplying by 1 minus the common difference 3 to the power of the number of terms, which is 5. So let's work at the numerators and the denominators. So 3 to the power of 5 is going to give us 243. So one take away that will give us a negative 242. Then 1 minus that's 1 minus 3, that's going to give us negative 2. So we work this out. Negative 242 divided by negative 2 gives a positive 121. Then we multiply that by 6 for our answer, and we get 726. Now let's just go back to our last example. Let's add them up and see what we get. So 6 plus 18 plus 54 plus 162 plus 486. All that together, it does give us 726. So we can see that the formula works. Another important example of these is when the nth term is going to give us some kind of fraction. So we can have something like 3 times 3 to the negative n. An alternative way of writing that is going to be 3 times 1 over 3 to the power of n. Now, if we generate this sequence, it's going to give us the first term n will be 1, so 3 times 1 over 3. That's going to give us 1. Then when n is 2, 3 to the power of 2 is 9, so it's going to be 3 times 1 over 9, which is 3 over 9, which is a third. Then when n is 3, 3 to the power of 3 is going to be 27. That'll give us 3 over 27, which is going to give us 1 over 9. What you might notice is the denominator is getting 3 times bigger each time. So what's happening with this sequence is each time we're actually dividing by 3. And another way of doing a divide by 3 is to write it as a fraction, which is why the denominator is actually getting 3 times bigger each time. Now, with these, you have another kind of formula, and this formula is sum to infinity. Because what's going to happen is, you'll notice with this sequence, 1, 3rd, and 9th, 1 over 27, they're getting smaller and smaller and smaller, these numbers. So there's actually a limit to how big this sequence can get, even if you add up all of these numbers until infinity, because the numbers will start getting infinitely small. So this formula is a multiplied by 1 over 1 minus r. So we're lacking the n part of this sequence. So if we try it out with this example, the sum to infinity, a is still the first term, which is 1. We'll multiply by 1 over 1 minus r, which is the common difference. Now, because it's dividing by 3 each time, we write it as a fraction. So we're going to write it as 1/3. So now we can start to work this out. So we have 1 multiplied by the bracket, and that's going to be 1 over 1 minus 1/3 is 2/3. Now, if you get a triple-decker bracket like this is really bad. We don't want to do this. Now, you can test it out on a calculator and see what happens. But what you can basically do in this situation is flip the fraction upside down. You get 3 over 2. So on a calculator, let's say types in 1 divided by 2/3. Maybe write it as a decimal, 0.6 recurring. It's going to give you 1.5 as an answer. And 3 over 2 is also 1.5. So what the sum to infinity tells us is that with the sequence 3 times 3 to the negative n, no matter how many items in that sequence you add together, you will never get higher than 1.5, because each time the number's getting smaller and smaller and smaller and smaller and smaller. The last thing to mention is that for all these questions, our starting point k was 1. If the starting point k was something else, let's say it was 2 or 3 or 4, they would use these formulas and we would subtract the terms that we don't want. So let's say that k was equal to 2, when to start adding from the second term of the sequence, you would follow this as normal, and then you would take away the first number, the first part of the sequence. Radians are an alternate way of measuring circles. So usually with degrees, a circle is 360 degrees. Now, when we look at radians, a circle is 2 pi radians. The reason for this is that 360 was just a really good number people chose because it's got lots of factors. You can divide it lots of different ways. So 2 pi is a way to kind of relate the measurement of a circle to some actual mathematics. There's actually a reason why we're using pi, whereas 360 was just kind of, used because it was a good enough number. Now, you can convert between the two. So to get from 360 to 2 pi, you need to divide by 180. 360 divided by 180 is 2. And you need to multiply by pi to get the pi on the end. And that will convert any number in degrees to radians. You can also go the opposite direction and convert from radians to degrees. To get from a 2 to a 360, you need to multiply by 180. And then we'll need to get rid of the pi, so we divide by pi. So to do those two things in either order, you can convert anything in radians into degrees. Now, as well as being able to convert them, perhaps using a calculator for this, there's also exact values you should know. So the exact values are 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Now, if you convert these into radians, you're going to get 0 radians, pi over 6 radians, pi over 4 radians, pi over 3 radians, and pi over 2 radians. And the reason why I've got pi in there and not a decimal, so for example, pi divided by 2 is 1.570796327. That number will continue in more decimal places. It's a rational number. It's not going to end. There's not going to be a pattern. So rather than writing out the whole thing, or as far as we can get, or even rounding it to be shorter, if we write the pi in there, it means we don't need to round. So we have our degrees and radians. Now, as well as memorising that, we need to memorise what the sin, cos, and tan of these are. Sine theta, cos theta, and tan theta. So at 0, sine is 0, cos is 1, and tan is 0. At 30, sine is a half, cos is root 3 divided by 2, and tan is 1 divided by root 3. At 45 degrees, sine is 1 divided by root 2, cos is 1 divided by root 2, and tan is 1. At 60 degrees, sine is root 3 over 2, cos is a half, and tan is root 3. Then at 90 degrees, sine is 1, cos is 0, and tan is not defined. There's not a solution for it. I guess in a way you could say it's infinity. If you look at sine and cos, you'll see sine and cos have got the same values, but in the opposite order. So if you can remember the sine values, if you flip them over, you've got the cos values. Knowing these exact answers is useful for a few reasons. So it can be useful if you're working with Surds, or it might be useful if you're working without a calculator. And so you want to work with a full level of accuracy without rounding. Trigonometry in a right angle triangle is going to involve a second angle being labelled. Then we've got the hypotenuse, the longest side, the adjacent, that's next to both labelled angles, and the opposite, which is the one opposite, the labelled angle that isn't the right angle. Now, if you have some values for these, then you're going to be able to use trigonometry to find the other missing value. Also, you should remember that the angle, we can label that theta. We have the acronym SOCAR TOA to help select a method, and each one of these references a triangle. So we have the SOA form of the triangle, and from left to right, you just go SOH. We've got the CAR form of the triangle, and again, you just go from left to right, CAH, and the TOA form of the triangle, left to right, TOA. Now, the O, the H, and the A correspond to which ones of the O, H, and A have in the original diagram. The S, C, and T refer to the angle. If you want to find a missing angle, theta, then look at the form of triangles. You cover up the S, C, or T. You look at what's left over, and you should have two letters on top of each other. So, for example, theta could be the inverse sine of O over H. That's what you get from the first form of the triangle. Or it could be the inverse cos of A over H. Or the angle could be the inverse tan of O over A. So that's what it means when you've got the letters on top of each other. If you're looking for the opposite, then we look at the form of triangles, you cover up the opposite, and whatever's left over is the maths you do. So from the first form of triangle, the opposite, if you've got S and H next to each other, that means the sine of the angle theta, multiplied by the hypotenuse. And you've also got that in the last form of the triangle. You cover up the opposite, what you've got left over is the T for tan. So you've got tan of the angle multiplied by the adjacent. For the side A, you cover up the A in the form of triangle. So for the first one, if you cover up the A, you're going to get that the adjacent is equal to the cosine of theta multiplied by H, because next to each other. But in the third form of triangle, you see A is in a different position, and it's O over T. See, the adjacent will be equal to the opposite divided by the tan of the angle. The last one to think about is the hypotenuse. So again, you cover up the hypotenuse to find it, and you look at what's left over in the form of the triangle. So if you cover up H in the first form of the triangle, you've got O over S. So that means that the hypotenuse is going to be equal to the opposite divided by the sine of the angle. You've also got H in the second form of triangle. If you cover it up, you've got A over C, so it's going to be the adjacent divided by the cosine of the angle. Now, you're only going to use one of the form of triangles, and it depends on what you've been given, what's been labelled. So it might be you're not given the hypotenuse at all, you're only given the opposite and the adjacent, so you can only use the third form of triangle in that example. And so you'd only be able to find out the opposite, the adjacent, or the angle, depending on which of the two of the three you're given as a clue. Now, you can also use trigonometry in non-right-angled triangles, and we have some formulas for those. Now, the way we'd label a non-right-angled triangle is that we would give a letter for each one of the angles. So we could call them A, B, and C. Then have a letter for the sides. And what we do is we name the sides the lowercase of the opposite angle. So we've got side A, side B, and side C. So lowercase for a side and a capital letter for an angle. So that brings us to the sine rule. The sine of an angle divided by the opposite side is equal to the sine of any of the angles divided by the opposite side. So these are all in the same ratio, and we can use this to find missing sides and angles. You can also do this the other way around. So you could have the side divided by the sine of the opposite angle. Another rule related to this is the cosine rule. The cosine rule is related to Pythagoras theorem. So in Pythagoras theorem, c squared is equal to a squared plus b squared. But this only works for a right-angled triangle. Now, if you don't have a right-angled triangle, you need to make an adjustment for the angle being different. And that adjustment is taking away 2 multiplied by a, multiplied by b, multiplied by the cosine of the angle c. This is also independent of the names of the variables. So we could, name the letters in another way around. And so we can write it in different ways. We can write a version that's b squared equals and a squared equals. So the way it works is the thing you're looking for, it's going to be the two other letters added together. So you're looking for b, it's going to be a squared plus c squared. You're looking for a, it's going to be b squared plus c squared. Then when you make the adjustment, it take away 2 of the squared signs, so 2ac or 2bc. And then the cos is always the angle related to the thing you're looking for. So you're looking for side B, it'll be cos angle B. You're looking for side A, it'll be cos angle A. The last thing you need to know for this is how to find the area of a triangle using trigonometry. Now, like the cosine rule related to Pythagoras theorem, this one's related to the area of a triangle. The area of a triangle is equal to a half of the base times height. Now, we don't have a base and a height in a non-right angle triangle because the base and the height have to be at right angles to each other. So let's just call them A and B. So that's the formula for a normal triangle with a right angle. If it doesn't have a right angle, you have to make an adjustment. And the adjustment's really easy. You multiply it by the sine of the angle of the side you're not using. So if you're using A and B as our sides, what the sine of C? And again, just like the cosine rule, you can do this with the other letters. So A could be half of AC, sine B, or you could have half of BC, sine A, as long as it's 2 sides and then the unrelated angle. So here we've got all the kind of GCSE trigonometry formulas on one page. And also, don't forget Pythagoras theorem, you'll need to use that sometimes. C squared is equal to A squared plus B squared. Trigonometric equations combine your equation solving skills with trigonometry. Now you might have something like sine theta is equal to 0.4. And this is something you can solve using equation solving skills. Now, we want to get theta on its own for this question. So the first thing to do is that we can do the inverse of sine to both sides. When you're using the kind of form of triangles of trigonometry, you use sine to minus 1 or cos to minus 1. This is practically what you're doing. So if we do the inverse sine of 0.4, we get 23.6 to 1 decimal place. And you might think, great, that's the answer. We do trigonometry with triangles. This is as far as you go. However, there are actually multiple answers for this. Now, the way you're finding multiple answers is you need to sketch a sine curve. So the sine curve is going to go from -1 to 0 to 1. We need to remember the way around a sine curve goes. Now, what you could do in a calculator is press sine 0, and that'll give you a coordinate you can point. Sine 0 is 0. Then you could do, say, well, what's sine of 90? The sine of 90 is 1. And then you could think, well, what's sine of, we'll go up in 90s, what's sine of 180? Sine of 180 is 0. Go up another 90, sine of 270 is -1. And sine of 360 is 0. So it gives you an idea of where the sine curve goes. Then we can join it up with a curve. And here we have a rough sketch of a sine curve. Now, you might want to label the x-axis. Well, I've got the y-axis labelled. So you might think, well, I've got 0 degrees, 90, 180, 270, and 360. Now, our answer is at 23.6 degrees, and that corresponds to 0.4. So 0.4 to be just below half. And what we can see is in between 0 and 360, 0.4 cuts through the curve in two different places. That means there's actually two answers. The first answer we have is right at the start, so it's in between 0 and 90. So this is our 23.6. We can think, well, from the start, we've gone in 23.6 degrees. Now, the symmetry with these curves, if we look in between 0 degrees and 180 degrees, there is a line of symmetry through this curve. So if we're 23.6 on the left-hand side, using the symmetry, the second value is also going to be 23.6 in. But this time going from the right-hand side, which is at 180. So 180 and take away 23.6 to go 23.6 before it will give us the second answer, which is 156.4 degrees. So this is all about, using your solving equation skills, but then also recognizing that when you do inverse sin, cos, or tan, there's going to be multiple answers. So let's look at a version with cos. So let's look at cos theta of, let's do negative 0.7. So we would do the inverse of cos to both sides, and that would give us that theta is equal to, so we're going to do the inverse cos, negative 0.7, and that'll give us our first answer, 134.4 degrees. Now again, there is going to be a second answer between 0 and 360, and we're going to have to draw something to find it. So again, you have to do this yourself. You have to sketch the curve between negative 1, 0, and positive 1. Then with angles, it's good to go with increments of 90 degrees. Eventually get to a stage where we remember how the curve goes. If you don't remember the curve, use a calculator. Type in cos 0, which will give you 1. Type in cos 90, which will give you 0. Cos 180 will give negative 1. And just putting these in will give you an idea of where the curve goes. And then you can sketch it. So it's going to go like this. Now, cos 0.7 is going to be down at the bottom, closer to negative 1 than 0. And we can see, again, it's going to cut through the curve in two different places. Now, we have the answer between 90 and 180, which is 134.4. So think about how we did last time. We've gone in from the left-hand side, 134.4 degrees. Now, the line of symmetry in a cos curve is different. In between 0 degrees and 360 degrees, the line of symmetry goes through the middle at 180. So when we say, well, 134.4 into the left-hand side, let's do the same thing from the right-hand side. This time I'm going to take away from 360. And we take 134.4 away from 360, we get our second answer, which is 225.6 degrees. We can do this with tan as well. So let's have a look at the tan of 0.5. So we do the inverse of tan to both sides. And that gives us that theta is equal to the inverse tan of 0.5, which is 26.6 degrees. Again, this is only our first answer. So we need to draw the graph to figure out what the second answer is. The calculator only gives one answer. So set up a y-axis for your curve between negative 1, 0, and 1. Set up an x-axis, 0 degrees, 90 degrees, 180, going up in 90 degree increments. And then sketch the curve. And again, if you're not sure how to sketch it, you can type tan 0 into your calculator, which will give 0. So first coordinate. Tan 90 will give us a math error. That means there's an asymptote here. The line does not go through 90 degrees. Then we can do tan 180, which is 0 degrees again. Tan 270, again, gives us a math error. And tan 360 is also going to give us 0. Now, this hasn't really helped us draw a curve, has it? So you might want to look at in-between values. Let's try going up in 45 degree increments. Tan 45 will give us 1. So we know the curve is going to go up like this. Add on another 45, we get 90. Add on another 45 to 90, and we're going to get 135. So tan 135 is going to give us a negative 1. Then in between 180 and 270, add on 45, we get 225. The tan of 225 is a positive 1. And this gives an idea of where the curve goes. So it's going to be something like this. Now I want tan to be 0.5. So if we go through at 0.5, we can see that we'll cut the curve in two separate places. Now we have the answer right at the start, which is 26.6. Now there's a special thing with the tan curve, and it's that it repeats every 180 degrees. So all you need to do is take the 26.6, add 180 to it, and you're going to get another answer. And that's 206 0.6 degrees. Now the next thing we need to talk about is a range. All of these questions have a range that's in between 0 degrees and 360 degrees. Now you won't always be given this. Sometimes you might have between 0 degrees and 720. And so for 720, you would make these curves go twice as long. So you draw them going up to 720. You could have it between negative 180 and positive 180. So you draw the bit of drawn here, but then you'd also go into the negative section as well. Now, regardless of how big this is, if you look between 0 and 360, you kind of set, because these curves, they always repeat as well. Every 360 degrees they repeat. And that's all three of these repeat every 360 degrees. So with the two answers that you've got, as long as you add and take away 360 degrees from them, you're going to get other answers. Because the big thing with these is that they kind of go on forever. So since the curves go on forever, we need to limit it somehow. Again, with 0 to 360 being the most common, but you might have others like I mentioned. The other thing is all of these are in degrees. You might also be asked this question in radians. There's two ways to do it in radians. You can do what I've done here, and then when you get your final answers, you can multiply by pi and divide by 180, and now your answers are in radians. The other way is that you can use the mode button on your calculator and set your calculator radians mode. There'll be a little there on the calculator display, and it'll give you the answers in radians straight away. Just make sure once you've done with that, change it back to degrees mode with a little D display. Otherwise, you get confused next time you use trigonometry and your sine, cos, and tan are giving you answers that are incorrect that you don't expect because it's in the wrong mode. With trigonometric identities, we can change some kind of expressions trigonometry into others. So, for example, if you take sine and you divide it by cos, you will get tan. So you can convert tan into sine and cos or vice versa using this method. Then we've got more complicated kind of trigonometry words. So we've got cosec. Cosec is equal to 1 over sine. Then there is sec. Sec is equal to 1 over cos. And there is cot, which is equal to 1 over tan. And these work the other way around as well. So sine is equal to 1 over cosec. Cos is equal to 1 over sec. And tan is equal to 1 over cot. Now, with the tan is equal to 1 over cot, we can write another identity, which is the following. Cot is equal to 1 over tan. Therefore, it's equal to cos over sine. And the whole thing with this, when you have 1 over something, what you've done is you've taken the reciprocal of the number. And so if you take the reciprocal of kind of like a normal number, a number on its own, then you're going to get a 1 over. And it kind of changes it into a fraction. But if it's already a fraction, like sine over cos, then when you take the reciprocal, it just flips the fraction upside down. This is our first set of identities. The next step is that sine squared theta plus cos squared theta is equal to 1. And by rearranging this, we can find out a few things. So, for example, sine squared theta is equal to 1 minus cos squared theta. Cos squared theta is equal to 1 minus sine squared theta. Then we can get versions with sec, cosec, and cot. So tan squared theta is equal to sec squared theta minus 1. Then we can say things like sec squared theta is equal to tan squared theta plus 1. Cot squared theta is equal to cosec squared theta minus 1. And cosec squared theta is equal to cot squared theta plus 1. So this is another method where you can take sin, cos, and tan, and you can kind of convert them into each other depending on what you need. We also have identities around about adding angles together. So sine, we've got angle A plus angle B, is equal to the sine of A multiplied by the cos of B plus the cos of A multiplied by the sine of B. And that works if you take away as well. There's a version for cos. The cos of A plus B is equal to the cos of A multiplied by the cos of B. Take away, so it's the opposite sign, the sine of A multiplied by the sine of B. And then if you've taken away the angle, then you'd be adding the angles instead. Then there's a version for tan. So you have tan angle A plus angle B. That's going to be equal to the tan of A plus the tan of B. And then it's all going to be divided by 1, take away, so the opposite sign, the tan of A multiplied by the tan b. If you take away the angles instead, it'll be a take away for the numerator, but it'll be an add for the denominator. Then we've got the double angle formulas. So the sine of 2 theta is equal to 2 sine theta multiplied by cos theta. It's also equal to, so we've got another alternative, 2 lots of tan theta, all divided by 1 plus tan squared theta. Then we've got options for this for cos and tan. So cos of 2 theta is equal to cos squared theta take away sine squared theta. It's also equal to 2 lots of cos squared theta take away 1, and 1 minus sine squared theta. And it's also equal to 1 minus tan theta, all divided by 1 plus tan theta. So we have lots of different options for changing the forms of these. There's also one for tan. Let's pop that up at the top. We've got a bit of room. Tan of 2 theta is equal to 2 tan theta divided by 1 minus tan squared theta. So we've got a big list here of different trigonometric identities, some of which you're going to have to be able to use to replace some trigonometric terms with others. Best thing to do here is look at the list, write it down, try and find the formula booklet for the exam you're doing, and then make sure which ones of these you need to remember for the exam and which ones are going to be given to you in the formula booklet. What you'll find is, though, you don't need to remember the whole list because some of these rearrange to make other ones. So you can remember a smaller list of these to make the rest. With differentiation from first principles, you might have a curve that's something like y equals x squared. It's going to be actually useful to look at what that graph is going to look like. So I'm going to draw some axes. Y equals x squared is going to look something like this. And what we mean by differentiation is you want to know what the gradient of this line is. Now the gradient is how steep the line is, and you'll notice that at the bottom it's going to be less steep, so let's highlight that in green. And at the edges it's going to be more steep, so let's highlight that in pink. So the steepness of the line depends on where it is. So how can we give it a gradient? How can we say how steep it is? So what we can do is we can find the gradient of just one part of the graph. Now it's not enough to do a single coordinate. We're going to look at the gradient in between 2 different coordinates. It's not exactly going to line up. It's going to be a straight line. It's not going to be a curve, but it'll give you a rough approximation. So what are these coordinates going to be? Well, it's called y equals x squared. So if you look at where the x coordinate is, of the first one, you call that x, because it's on the x-axis. Then the coordinate on the y-axis that corresponds to it, that's going to be x squared. It could be y, but we know that y is equal to x squared. So our first coordinate is going to be x squared. So then we look at the next coordinate. Now, the next coordinate is going to come down a little bit further along the x-axis. So what we do is we can call this x plus h. We've got a distance of h in between x and our next coordinate on the x-axis. And we'll just say it's an unknown number because we don't really know how far along we've gone. So the x-coordinate is going to be x plus h. What's the y-coordinate going to be? So again, y is equal to x squared. So if it's x plus h, we need to square that. So we take our x plus h and we square it. So let's write it in the coordinate. And having it in the brackets and squaring the entire thing is really important because then that gives us a quadratic that we can expand later on. So now we have our 2 coordinates, we've got to think about how we find the gradient. Now, in general, to find the gradient of anything, it's the change in y over the change in x. The way that works with 2 coordinates is you take one of the y coordinates and you take it away from the other y coordinate. It doesn't matter which way around the 2 coordinates are, as long as you're consistent. So whichever you pick first for y also has to be the first pick for x. And you do the same thing for x. So what we can do is we can substitute into this formula to find out the gradient in between these 2 coordinates. So our second y coordinate was the one in brackets, x plus h all squared. And then we're taking away the first y coordinate, which was x squared. We're dividing that by the second x coordinate, which is x plus h. And then we're taking away from that the first x coordinate. And so what we're going to do now is expand the brackets and clean this up. So you should know how to expand a quadratic. X times x is x squared. X times h is going to give us xh. H times x is also xh, we'll have two of those, and h times h is h squared. And then we're taking away x squared. Well, we've already got an x squared, so that'll cancel out to give us 0. Then for the denominator, x take away x will give us 0, so we're only going to have the h left. We can also divide through by h because both terms of the numerator have got a h and there's a h on the denominator. So we take a h out of both terms, 2xh becomes 2x, and h squared becomes h. And so we've got an expression that represents the gradient in between the two coordinates. Now, what we're going to do next is a little bit tricky. So if you look at the graph, the distance between the two coordinates on the x-axis was h, and that was just a random number chosen. We don't even know what the number is. That's why we labelled it with a letter. Now, imagine you make the distance between x and x plus h smaller. You make it half as big. Is that going to change our calculation here? And it's not. It just means that h is going to be plus a smaller value. What we can do is we can reduce the distance between the two coordinates more and more and more. And the more we reduce the distance between them, the more accurate our gradient's going to be. Because at the moment, it's a straight line on a curve, but the closer together they get, it's going to be, less inaccuracy making that straight line on the curve. And what we do is we say that there's going to be a limit as h approaches 0. And so what's going to happen is eventually these two quadrants will move them so close together that the value of h is completely irrelevant. And if we have h approach 0, then we get only 2x on its own. We get rid of the h. And what you'll find is that having h approach 0 and go away, what's left over, the 2x, actually represents the gradient of the curve. Now, it's not a number like you'd have before. With a straight line, the gradient's going to be a whole number. It's going to be a 2, steepness of 2, a 5, steepness of 5, steeper, or you can have steepness over a quarter, and that wouldn't be very steep at all. You get a number. This has got an x in it. And what it means is, if you substitute in the x, then it's going to give you the gradient no matter where you are on the curve. So, for example, at the bottom, where it's not very steep, x is going to take a smaller number. So I'm just going to highlight that in green like I did before. So let's say x is 1. Then 2 times 1 is 2. It's a gradient of 2, which is, vaguely steep. It's not too steep. If you're right in the middle, the flattest part, that's when x is 0. And then your gradient's 0. That's not very steep at all. Now let's look at the edges. If we imagine these edges are when x is like 10 or negative 10, when you substitute 10 in for x, you get 2 times 10 is 20. Well, that's really, really steep. And so you can see it working. You substitute in x, you get the gradient at that point. So this is how you differentiate from first principles. Now, we've done this for y equals x squared, and that's why our second coordinates were squared. Now, you can do this for other things as well. You can even do it for trigonometry, you can do it for more complicated curves, you do it for cubics, y equals x cubed plus 2x plus 8, whatever it is. And all that happens is the x coordinates will be exactly the same, x and x plus h, but the y coordinates will have a different transformation based on what you're doing. But if you just follow the process at the end, as long as h approaches 0, then you are going to get to the gradient. Now, with differentiation from first principles, y equals x squared is differentiated to 2x. And we said when you differentiate, you get the gradient of the line. So the gradient of y equals 2x is the difference in y over the difference in x. And this is where we get our differentiation notation from. Difference in y over difference in x. Now, you don't actually have to go through differentiation from first principles for every single question. There is a shortcut. And if you look at the question and the answer, you might be able to see it. You might be able to see that the power on the x has gone down by 1. We've gone from x squared to x to the power of 1. There's no 1 shown, but there's no power on an x. It just means the power of 1. So that's hidden information. The other thing is, it was the power 2, and now we've got a 2 at the front. And there is a connection there. So let's look at the general rule for differentiation. So if we say that y is equal to axb, so the power is b, a is a coefficient on the x, then the difference in y over the difference in x, the gradient is going to be equal to, so you multiply the a and the b together, so we can write ab for that, and then the x, the power is going to go down by 1, so it's the power of b minus 1. So if we apply that to what we've just done, we can see the power goes down by 1. Now, with y equals x squared, there wasn't an a. There wasn't a coefficient on the x. Or was there? If there isn't an a, it's just going to be 1. We have 1 x squared. So you do have to deal with hidden information in these questions. We've got the hidden 1 in the 1x squared, and we've got the hidden power 1 in 2x. So again, two things. The power has gone down by 1, and we've multiplied the coefficient on the x by the old power. You can also differentiate a second time. We call it d2y over dx squared. So if y equals is a line, and differentiate it once, dy by dx, gives you the gradient, d2y by dx squared, the second derivative, that's the rate of change of the gradient. It's how the gradient changes over time. And you just follow the same process. So we're going to reduce the power by 1. So x has gone down from 2 to 1, now it'll go down to 0. And then we multiply the coefficient at the front, the 2, by the old power, 1, and 2 times 1 is 2. So it's actually going to stay as 2. Now, when you have power 0, anything to the power 0 is 1. So effectively, this is saying 2 times 1. So altogether, it's actually just 2. Now, with this, we've only differentiated one term, but you can differentiate multiple terms together as long as they're separated by plus and minus. So we can have y equals x cubed plus 2x squared plus 3x plus 4, just as a random example. So we differentiate once to get the gradient. Here's what we do. Each time the power on the x is going to go down by 1. So x to the power of 3 becomes x to the power of 2. X to the power of 2 becomes x to the power of 1. X to the power of 1 becomes x to the power of 0. And we'll look at the last one in a moment, but I guess you could say with the plus 4, it's going to become x to the power of negative 1, because there's no x on 4, so it'll be x to the power of 0. So that's the first bit dealt with. The second bit is you multiply the coefficient on the x by the power. If there's no coefficient, it's going to be a 1. So 1 times 3 is 3. 2 times 2 is 4. 3 times 1 is 3. And then with this one, this was x to the power of 0. So 4 times 0 will actually give us 0. Now, this isn't really how we write algebra. So there's some information that's going to be hidden. So just like it's a 1x cubed, and it's a 3x to the power of 1, the hidden information here is we're not going to show the power 1 on 4x to the power of 1. We don't show x to the power of 0 because it's just equal to 1, and 3 times 1 is 3. And we're also not going to show anything with a coefficient of 0, because it's got a coefficient of 0, you times in by a 0, so no matter what the rest of it is, it's going to be 0, so we don't write it down. So now you might be able to see the final answer here. It's going to be 3x squared plus 4x plus 3. Now, it's worth us looking at this at the moment and just looking at kind of which terms disappear. So, for example, the plus 4, if you've got a whole number on the end of something and you differentiate a whole number, you get 0. Because whole numbers have got x to the power of 0 on them effectively, even though we don't write it down. So you multiply them by 0, so they go away. The next thing is, if you differentiate something like 3x, so a number with just an x to the power of 1, then you just drop off the x. 3x has become 3. It's only squared and upwards where you can use the full method and show all the information, where you multiply the coefficient by the power, and you can reduce the power by 1. Just take note that when you differentiate something that's squared, it's going to become power 1, and we don't write down power 1, so you just write x. So there's a few things to look out for there. Now, you wouldn't write all the hidden information down every single time, so if we differentiate a second time for the rate of change of the gradient, you're going to be able to do this in your head without any extra working out, really. So we're going to do 3 times 2 is 6, reduce the power by 1. 4x is going to become 4, and the 3 is going to go away. And it's actually that quick. You don't need to write all the rest of it down. So again, whole numbers disappear. It's gone. Anything with an x, the x is going to drop off. And then with powers 2 or higher, you go through the full method. Now, there are some special cases in differentiation, because it's not just kind of normal algebra you're going to be differentiating. There's also another way to show it, where rather than writing y equals, you can write f of x. Function of x is equal to. Then the differentiated version would be f dash x. So you can see it written both ways. So firstly, you can differentiate trigonometry. So if you have sine of x and you differentiate it, you get cos of x. You can also change the angles. The x is the angle. Now let's say we've got a more complicated angle. Let's say we've got the sine of 2x. We differentiate, the angle's going to stay the same. But what is going to happen is the coefficient on the x is going to pop out onto the outside as well. So you have sine of 2x, differentiate it, you get 2 cos 2x. The same thing happens with cos. So let's say we've got cos of 3x. When we differentiate it, when you differentiate cos, you get sine. The angle doesn't change, it'll still be 3x, but like from going from sine to cos, the 3 is going to pop out. So it's going to be 3 sine 3x. Another thing is, it's just not as simple as differentiation being the opposite of itself. It's not. So when you differentiate cos, you actually get a negative sign. We can also differentiate tan. Let's say we've got the tan of 4x. When you differentiate it, you get something called sec squared. The angle's not going to change, but the coefficient on the x is going to pop out, so we're going to multiply by that. If there's already a coefficient on this, then that will be multiplied as well. So let's say we've got 2 tan of 4x. Then when the 4 comes out, we'll multiply the 2 to give us 8. Sec squared is something you'll go through when you get onto the more advanced trigonometry, by the way. Another thing you might see, logarithms. So if our function is ln x, then when you differentiate that, you actually get 1 over x. You can also have other numbers involved in this. So let's say a function of x is 2 ln x cubed. If you've got a power on the x, that's going to come out as well. So when you differentiate it, you would get 6 over x. 2 times 3 gives us 6, and we're still going to be over x. If you have an exponential, so let's say we've got 4 to the power of x, when you differentiate that, you get somewhat of an odd answer. So the 4 to the power of x stays, but it's going to be multiplied by ln 4. The last special case we'll look at is there's a number called e. And e is an irrational number like pi. And like pi is 3 and a bit, e is 2 and a bit, but the decimal places don't repeat, there's no pattern, but they do go on forever. Now, if you raise it to the power of x and you differentiate it, something really interesting happens. Differentiating e doesn't change it. It stays the same. So effectively, it kind of represents its own gradient. Now, you can have other numbers involved in e. So, for example, we could have 2e to the power of 4x. And when you integrate that, what's going to happen is the coefficient on the x, just like with trigonometry, that's going to come out. 4 times 2 is 8, but then the e part doesn't change. It's still going to be e to the power of 4x. So these are some special cases you'll see for differentiation. Some you'll see more than others. The trigonometry ones are going to be the most common ones that you'll see. If we have a curve, let's say it's y is equal to x squared, and we have a little look at what that might look like. So we have an x and y axis, we have the curve. You might want to find something called tangents and normals. So what do we mean by tangents and normals? So a tangent is a line that comes down and it touches the curve at exactly 1 point. Now, a normal is a similar concept, but a normal is at a right angle to the tangent. It also crosses the curve at that 1 point. It might cross it at another point further back as well. But again, the point of this is it's at a right angle to the tangent. So this is the normal. And you might be asked to find the equation of these lines. You'll also likely be given the coordinate of the point where this happens. So let's say for this question, this one's at the coordinate 5, 2. So let's look at how we find the equations of the tangent and the normal. So the first thing to think about is that we've got our curve, y equals x squared. And if we differentiate it, we're going to get the gradient of the curve, or something that represents the gradient of the curve. So we're going to reduce the power by 1, x squared becomes x to the power 1, and we're going to multiply the coefficient by the power. So if there's no coefficient, it's a 1, 1x squared, 1 times 2 is 2. So we've got something that represents the gradient. Now, because we've got a coordinate, we can find the gradient at the point 5, 2. So we can substitute in the x coordinate 5, and that'll give us the gradient at that point. 2 times 5 is 10. So we know at that point, and that point only, there is a gradient, there's a steepness of 10. Now this tells us something about the tangent. The tangent has the same gradient as the curve at the point where the tangent is. So the tangent is going to be y equals mx plus c. And we know what the gradient is. Y equals 10x plus c. All we want now is a value of c. And to do that, again, we're going to substitute in the coordinates at the point, the 5 and the 2. So y is going to be equal to 2. Then we've got the 10 lots of x, and x is 5. And we've got the plus c, which is what we're looking for. This means that 2 is equal to 50 plus c. So we take 50 away from both sides. That means that negative 48 is equal to c. So we can see the tangent is y equals 10x minus 48. We can use a similar method for the normal. So again, for the normal, we know it's going to be y equals mx plus c. It's a straight line. And we know what the gradient is. The gradient is y equals 1 over 10x, or either negative 1 over 10x plus c. You might be thinking, well, where has the 1 over 10x come from? And it's just the same as parallel and perpendicular lines. So the normal is perpendicular to the tangent. It's at a right angle. So we take the negative reciprocal of it. We can follow the same process to get c. So we're going to substitute in 5 and 2. So y is 2. The gradient's negative 10th. We're going to multiply that by x, which is 5. And then we have the plus c. That means 2 is equal to negative a half plus c. Because 1 over 10 times 5 is 5 over 10, which cancels down to a half. If we add a half to both sides, that means that 2.5 is equal to c. So now we can write down the equation of the normal. Y is equal to negative 1/10 of x plus 2.5. So the big thing to remember here is that the tangent has the same gradient as the curve. The normal, being at a right angle to it, is a negative reciprocal. Make it negative. If it's a whole number, put it over 1. If it's a fraction, then you flip the fraction upside down for the reciprocal. We can use differentiation to tell us things about the turning point of a curve. So let's say we've got the curve y equals x cubed minus 2x squared plus 4. Now, if we draw a quick sketch of what this might look like, a cubic is going to look something like this. But we don't know exactly where this is going to fall on the x and the y axes. And so this is what we're going to try and find out. Now, before we even start, there is one thing that we're going to know, and that is with a plus 4 at the end, it means that the y-intercept, where the curve goes through the y-axis, is going to be at 4. So we can find that straight away. Now, if we differentiate twice, so dy by dx, we'll get some information. And if we differentiate another time, d2y by dx squared, we'll get another set of information. So let's do it. So 3 times 1 is 3, reduce the power by 1. 2 times 2 is 4, reduce the power by 1. And any whole numbers are going to go away. Differentiating again, 3 times 2 is 6, reduce the power by 1. And it's just the next term, we're just going to keep the coefficient. So what information can we get from these? Well, the first thing is we're probably going to want to know where the turning points of the curve are. Now, to find those, these are when the gradient is equal to 0. And so what we can do is we can say, well, if the gradient is 3x squared minus 4x, we can make it equal to 0, and then we can factorize it to find those points. Now, you might be able to factorize it by inspection or completing the square, but you'll always be able to do it by using the quadratic formula. I'm not going to go through that here because we've revised that already. But if you do the quadratic formula, you're going to get that x is equal to 0 and x is equal to 1 1/3. So they are going to be our turning points. So we know this one's going to be 1 1/3. Now, the other one, surprisingly, is 0. So really, we should have had that a little bit further over. So we're not really sketched this right. You can see it's not x equals 0 at all. It should be a little bit further over. And what that means is that the y-intercept and one of the turning points are actually the same coordinate at 0, 4. If you want the y-coordinate of the 1 1/3, then what you can do is you can substitute it back into the y equals, and that would give you the y-coordinate as well if you wanted it. Another thing you might want is something that we call the point of inflection. The point of inflection is in between the kind of two peaks. So it's a bit where we stop being the first curve and we start being the second curve. Now for that, that's where the second differentiation is equal to 0. The rate of change is equal to 0 because it's in the middle of going up and going down. So we're going to say that 6x minus 4 is equal to 0, and we can solve the equation. We can add 4 to both sides. We can divide by 6. X is 4/6, which can simplify to 2/3. So we know that the point of inflection, the bit where one curve turns into the other curve, is going to be at 2/3. Another thing you might want to know is we've got the kind of the top and bottom of the two curves, 0 and 1 1/3. We only know which one's at the top and which one's at the bottom because I've actually sketched out the graph correctly. But you might not actually know which way around this cubic is. So how do we know that 0 is at the top and 1 1/3 is at the bottom? So what we do for this is, again, we're going to substitute into 6x minus 4. We're going to have 6 lots of 0 minus 4, and we're going to have 6 lots of 1 1/3 minus 4. So substituting the x coordinates of the top and the bottom into the second differentiation, because this is the rate of change. And so what we want to do is look at what the rate of change is at these points. Now at 0, 6 times 0 is 0, take away 4 is negative 4. We've got a negative rate of change up there. What it means is at 0, the rate of change is negative 4. That means the curve is starting to come downwards after it. So we call this a maximum. With the next one, we've got 6 times 1 1/3, which gives us 8. And then we take away 4 and we get 4. It's a positive 4. That means that at 1 1/3, the rate of change is 4. That means that the curve is going to start going upwards. So we call this the minimum point. So these numbers about what's happening next when you read the graph from left to right. So if on the right-hand side it's minus 4, you must be at the topmost part that's going down next. So it's kind of the opposite way around you think. If the rate of change is going to be 4 next, then you must be at the very, very bottom for it to be going upwards afterwards. One last thing is, 0, the top of that curve, isn't actually the top of the graph because we can see on the right-hand side it actually goes up the cubic. It goes down as well on the other side. So these aren't actually the maximum minimum points. We call them the local maximum and the local minimum because they're the highest and lowest points around about where they are, but later on there are going to be even higher points. And let's get this labelled on the graph. So 1 1/3 was the minimum point and 0 was at the maximum point. Another thing you can do, and it's not part of differentiation, but if you take the original x cubed minus 2x squared plus 4, if you do that equal to 0 and you use the quadratic formula, or again any other method you can use to factorize, this is going to give you the x-intercepts. Now for this one there's only one, and so it's going to give you x is equal to, and it's about negative 1.1 to 1 decimal place. But often with cubics you're going to get 3 of these, and it's going to cross over the x-axis up to 3 times. So that's something else you can look for as well. So there's lots of different methods from different areas of maths, but the key things are the differentiation will give you the turning points. It'll tell you which one's the local maximum and which one's the local minimum. It'll also tell you the point of inflection, which is the bit in between the 2 turning points. Differentiation usually works when you've got single terms or those terms will be separated by a plus or a minus. If you've got single terms or multiple terms, then you can differentiate. Now, sometimes you might have, in effect, terms that are separated by other things. So let's say they're being multiplied together. Now, for that, you're going to use the product rule. So let's have a look at an example first. So you might have something like y equals, and then you might have 2x squared plus x multiplied by x cubed plus 3x squared. So you can see here you've kind of got 2 terms, but they're being multiplied together. And so this is where you use product rule. So product rule is, if you're differentiating u multiplied by v, then your answer is going to be equal to v du by dx plus u dv by dx. Now, I like to write that in a simpler way. So I'll show you my way of writing it. So we're saying if we want to differentiate u multiplied by v, then what we're going to end up with is v multiplied by the differential of u plus u multiplied by the differential of v. So what we want to do is we want to find these different bits. We want to find what u is, we want to find what v is. So u is going to be our first bracket, 2x squared plus x, and v is going to be our second bracket, x cubed plus 3x squared. And we can see with a little dash, all that means is you differentiate it. So u dash, 2 times 2 is 4, reduce the power by 1, and the x is going to differentiate to 1. Same thing with v. 3 times was no number, so just have the 3, reduce the power by 1. 3 times 2 is 6, and reduce the power by 1. And so we've got our letters, and we've got our differentiated version of the letters. So now we just substitute. So we want v times u dash. So v is x cubed plus 3x squared. And we're going to multiply that by u dash, which is 4x plus 1. We're going to add to that u times v dash. U is 2x squared plus x. And v dash is 3x squared plus 6x. Now we just need to expand the brackets. So we've got quadratics here in the way they're set up. So x cubed times 4x is going to be 4x to the power of 4. X cubed times 1 is going to be x cubed. 3x squared times 4x is going to be 12x cubed. And 3x squared times 1 will be 3x squared. Moving on to the second bracket, 2x squared times 3x squared is 6x to the power of 4. 2x squared times 6x is going to be 12x cubed. X times 3x squared is 3x cubed. And x times 6x is 6x squared. So now we need to write down our final answer. Let's look at the power of 4s first. We've got 4 and 6. That makes 10. 10x to the power of 4. Then let's look at cubes. So we've got 1, another 12, so that's 13. Another 12, so that's going to be 25. And another 3, that's going to be 28. So 28x cubed. Then we'll look at squareds. We've got 3x squared and 6x squared. That's 9x squared. And so that is going to be our final answer. 10x to the power of 4 plus 28x cubed plus 9x squared. Now, this is probably one of the most complicated ones you can get with just kind of x's and powers. Usually it's going to be simpler, so it cancels out more when you do your differentiation. You can also get this with things like trigonometry in. And when you do things like that, just have a look back at the special cases for differentiating trigonometry, but it's going to work the same way. The quotient rule is when you want to differentiate, but the numbers aren't being added or subtracted like normal differentiation. They're not being multiplied like product rule, they're being divided. So you might have something like y equals 2x cubed plus 3x squared, all divided by 8x plus 5. Now, to use quotient rule, what you need to do is you want to differentiate. You've got u divided by v, so something's being divided by something else. And so the answer is going to be v multiplied by du by dx, take away u multiplied by dv by dx, and it's all going to be divided by v squared. Now, again, a little bit of a complicated notation. It's why I like to write it out and a little bit more simple. So let's look at my way. So I would say if you've got u over v and you want to differentiate them, then you're going to do v multiplied by the differential of u, take away u, multiply the differential of v, all divided by v squared. So first we're going to figure out what u and v are. So u is going to be the numerator, 2x cubed plus 3x squared, and v is the denominator, 8x plus 5. So u dash, we are going to differentiate the numerator. 2 times 3 is 6, reduce the power by 1. 3 times 2 is 6, reduce the power by 1. Same thing for v. 8x becomes 8, and the 5 is going to go away. And now we can substitute. So we want to do v multiplied by u dash. So v is going to be 8x plus 5. And u dash is 6x squared plus 6x. So let's put these in brackets to be multiplied together. We'll take away from that u, which is 2x cubed plus 3x squared, multiplied by v dash, which is 8. And it's all going to be divided by v squared, which is 8x plus 5 multiplied by itself, it's squared. So now we need to expand all of the brackets. So 8x times 6x squared, it's going to be 48x cubed. 8x times 6x is going to be 48x squared. 5 times 6x squared is going to be 30x squared, and 5 times 6x will be 30x. We're taking away from that 2x cubed times 8 will be 16x cubed, and 3x squared times 8 is going to be 24x squared. Remember, we're taking away the second bracket, so these are going to end up being negative. That's all going to be divided by, I've got the quadratic to expand, 8x times 8x is 64x squared. 5 times 8x is going to give us 40x, and 5 times 8x is another 40x, and 5 times 5 is 25. So I'm going to collect like terms and try and simplify this, but the quotient rule of this part is done now. It's just kind of tidying it up. Let's look at the x cubes first. We've got 48x cubed, and then we've got a negative 16x cubed. So 48 take away 16 is going to give us 32. Then we can look at the x squared. So we've got 48. We're going to add on 30. And we're going to take away 24. That's going to give us 54x squared. Then we've got the x term, there's only one, 30x. Then the denominator, we've got 64x squared, 40 plus 40 equals 80x, and the 25. Now at this point, there's things you can do. So what you might want to try is you could try and factorize this, and if you've got the same factor on the numerator and the denominator, then you can divide by it and make it simpler. You might just be able to look at the whole thing and go, oh, every term's got an x in, I can divide through by x, or every single coefficient is even, so we can divide through by 2. So there's things you can do at this point onwards, but then that's outside of quotient rule. This is just a simplifying algebra. So I'll leave it here. The chain rule is when we differentiate, and the different bits of your expression are separated by a plus or minus, with for normal differentiation. They're not separated by multiplications for product rule, or divisions for quotient rule. The chain rule, there's going to be some kind of other function. So it could be a power, or it could be a bit of trigonometry or something. So for example, you might have y is equal to, and you could have something like 4x cubed plus, let's say, 3x squared. And this itself is going to be raised to a power. So this could be to the power of, let's say, 5. So to use a chain rule, what you say is dy by dx is equal to dy by du multiplied by du by dx. You might be thinking, what's this u bit about? Well, it refers to some substitution. Now, it might be easier to write this in a different way. So if you've got a function of x, and x is another function of x, then we can change that to be the differentiated version of that function, that is a function of g of x, multiplied by the differentiated version of g of x. And again, that still looks a little bit complicated. So let's have a look at it in practice and see if it makes more sense. So our function of x is what we are actually doing to this equation, and it's being raised to the power of 5. So it's going to be something to the power of 5. Now, rather than saying, oh, it's something to the power of 5, we're going to actually use a letter for this, and we're going to use u. That's where the u came from before, and we put that into the x. So our function, 4x cubed plus 3x squared, it's being raised to the power of 5. Now, what's inside the brackets, what's being, what the function's being applied to, is our g of x, and that's 4x cubed plus 3x squared. So we've separated what's inside the brackets and what's outside the brackets. And we've done this with a power in this situation. You can also have this with trigonometry. So when you kind of differentiate the angle in trigonometry, then the f something might be sine or cos rather than a power 5, with the x bit being the bit inside the trigonometry brackets. So now we need to differentiate. So differentiating f of u. So we know we're going to reduce the power by 1. So 5, it's going to become 4. And we multiply by the old power. So we get 5 lots of u to the power of 4. Then we differentiate g of x. So 4 times 3 is 12, reduce the power by 1. 3 times 2 is 6, reduce the power by 1. And I've got the differentiated version of g. So now we just need to substitute. So what this says is the differentiated version of f, which was 5 of our function to the power of 4, we're going to put g of x back into that, which was 4x cubed plus 3x squared. Then we're going to multiply that by the differentiated version of g, which was 12x squared plus 6x. Multiple terms there, so let's put it in brackets. So for our final answer, we'll try and clean this up. We've got the whole number 5 at the front. We've got one set of this bracket, and we've got 4 sets of this bracket. So we've applied chain rule here. We've still got quite a complicated expression at the end. There might be more steps here. You might want to take more things out as factors. You might want to expand the brackets. It all depends on what question you're being asked. But this is a chain rule part of the question. Integration is the reverse of differentiation. So let's say we have y equals 2x squared plus 3x plus 4. If we were to differentiate this to get the gradient, then we'd multiply the coefficient by the power. 2 times 2 is 4, and reduce the power by 1. Anything with an x, we're just going to have the coefficient left over, and any numbers are going to go away. So we get 4x plus 3 is the gradient of 2x squared plus 3x plus 4. So we have differentiated. So how do we integrate? How can we go in the opposite direction? So we think about differentiation. There's a couple of features. First thing is the power goes down by 1, and then you multiply by the old power. So integration is going to be the opposite. You increase the power by 1, and you divide by the new power. And we can write a general version of this. So if we integrate, this is the integral symbol. If we integrate, let's say, ax to the power of b, then we put dx at the end as well, which is part of the notation for this. Then the answer, you increase the power by 1, so b becomes b plus 1, and then you divide by the new power. So a is going to be divided by b plus 1. So yeah, differentiation, take 1 away from the power. Integration, add 1 to the power. Differentiation, multiply by the old power. Integration, divide by the new power. So let's give it a go. Let's see what this does. So if we're going to integrate 4x plus 3, then what we do is we're going to increase the power by 1. So the x becomes x squared. And then we need to divide by the new power. So 4 is divided by the 2 to get us 2x squared. Then for the 3, we increase the power. If there's no x there, then it's x power 0. Increase it by 1. We get x to the power of 1. And then we divide by the new power. Well, the new power is a 1. 3 divided by 1 is 3. And that's it. And now if you compare this to differentiation, we're actually missing the plus 4. So when you work backwards, it isn't actually a way to get that plus 4 back. So what we do is we write plus c, plus a constant. There might have been a number, but we can't actually work backwards to find what it is. So there is a flaw with integration. Now, one way to make up for this is something called a definite integral. What we just did there is a indefinite integral. So if we're going to integrate our 4x plus 3, what you might be given are numbers on the integral. And let's have a look what this means. So we're going to do the integration, which we already know is 2x squared plus 3x plus. So what this means is you're actually substituting those numbers. So the first one we're going to substitute in is the 3. That means we have 2 lots of 3 squared plus 3 lots of 3 plus c. Then we're going to take away, which we're substituting, 2 lots of 1 plus 3 lots of 1 plus c. And then we can work this out. So 3 squared is 9, times 2 is 18, 3 times 3 is 9, plus c. Then we're taking away the second bracket. 1 squared is 1, times 2 is 2. We're taking the second bracket away, so we take that away. 3 times 1 is 3, but again, we're taking away. And then we've got the plus c. And again, because we're taking away the second bracket, we have to take away the plus c. And if you do that, what you'll notice is we've got a positive plus c and a negative plus c, and they're going to cancel out. So you can actually solve a definite integral even if you don't know what C is. So we can add these up. 18 plus 9, take away 2, take away 3, and altogether we get 22. So we get a full answer without needing to know every single bit of the thing that we integrated. Now you might be wondering, what does this represent? So let's draw it on a graph and see what it actually means. So we're going to have x and y coordinates. We are going to have the curve, which is our 2x squared plus 3x plus 4. So what does the definite integral mean? Well, we substituted in 3 and 1. So what this means is you can have 1 on the x-axis, and you're going to have 3 on the x-axis. So this is what we're looking in between. And what happens is when you integrate, what you actually do is you're finding the area underneath the curve, between the curve and the x-axis. So everything I'm highlighting in blue, this is our answer, this is what we're looking for. And that is what we discovered was 22. So if we label it, this has an area of 22. This then takes us to another function of integration, as well as being the opposite of differentiation. And so you can turn a gradient back into the line, like we did with our example. You can also use it to find the area between the curve and the x-axis if you integrate something that's y equals. Now, there are special cases for integration, and it's basically the same with differentiation, but the other way around. Let's start off with trigonometry. So if we have f dash x, which is cos of x, then when we integrate it to get f of x, when you integrate cos, you get sine. It works the same way that it does with differentiation. Now you can also have numbers on the x. So let's have a look at, so let's say we have cos of 2x, then when you integrate it, you're going to get sine 2x, again the angle's not going to change, but with differentiation you'll be multiplying by the 2. Well, integration's the opposite, you need to be dividing by the 2. So you end up with a half of sine 2x if you do that. You can integrate sine, so let's look at sine of 3x. So when you do this, if you remember differentiation, when you differentiated cos, you got a negative sign. So this is the opposite of that. So if you integrate sine, you're going to get a negative cos. Again, the angle's not going to change, but you're going to divide by the number. So it's a 3, so we are dividing by 3. Then we do the same thing with tan. Now, with tan, because it's the opposite, we'll start off with sec squared. And let's say we've already got a 4 on the outside. So when you integrate it, when you integrate sec squared, you get tan. The angle doesn't change, but you divide by the angle. And we've already got a 4 on the outside, so 4 divided by 4 is 1. So we just get tan of 4x. We also have the reverse of differentiating logs. So if f of x is 1 over x, then when you integrate it, you're going to get ln x. If f dash x was something like 5 over x, then f of x is going to be ln x to the power of 5. We also have e. If f dash x is equal to e to the power of x, then when you integrate it, again, e is that special number where when you differentiate it, it stays the same. And it's the same for integration. However, if you have some extra numbers involved in it, they can get involved. So for example, e to the 3x, when you integrate it, you're actually going to get a third of e to the 3x. So the e part hasn't changed, the x part hasn't changed, but you bring out the 3. If it's differentiating, you multiply by it. If it's integration, you divide by it. Another useful thing to show is you can have things like, you can have 2 over the square root of x. Now, there aren't any special rules for this. It's just a matter of rewriting this in a more reasonable form. So we can say, well, this is equal to 2 over x to the power of half. Square root is the same as x power half. And then we can bring that up to the top and say it's 2 to the power of x to negative half. So any powers on the denominator can be brought up to the numerator. Now we've got it written like this, now we can integrate it safely. And we just use our normal rules. We increase the power by 1. So x to the negative half becomes x to the positive half. We've added 1. And then we divide by our new power. So it's going to be 2 divided by a half. You can write that as a fraction, for example. If you write it as a decimal, 2 divided by a half. How many halves are in 2? There are 4 halves in 2. So you can get some tricky things going on in that situation. Another way to divide by a half is to multiply by its reciprocal. Flip the fraction upside down, you get 2 over 1, which is 2. So 2 times 2 gives you the 4 as well. So you're trying to integrate, you've got some really funny notation, you've got fractions, you've got roots. Try and change them into a single line like I've done here, and then you should be able to integrate. Integration by parts is when the different terms that you're integrating are separated by a plus or a minus. Maybe they're being multiplied together. So, for example, let's say we've got y is equal to, and we could have something like x minus 3, and we could have x squared plus 5x. So how would we integrate this? So using integration by parts, a simple way to write it, integral, if you've got u multiplied by v dash, then that's going to equal u times v, take away the integral of v times u. So it looks pretty complicated. Let's try and identify what u and v are. So u is going to be one of our brackets. Let's just say it's the first bracket, x minus 3. So we can differentiate it to get u dash, because we need that as part of our formula, which would be 1. V dash, that's how it is in the formula, is going to be our second bracket. That's x squared plus 5x. So if we integrate it to get v, we're going to increase the powers by 1 and divide by the new power. So we should get something like this. So now we can substitute. So for our answer, we're going to have u times v. That's going to be x minus 3 multiplied by a third of x cubed plus 5 halves of x squared. Take away from it the integral of v times u dash. So v is a third x cubed plus 5 over 2 x squared. And then u dash is 1. So we multiply it by 1, it's not going to change. And so now we need to integrate that for our final answer. So the first part isn't going to change here, but the second part is. So we need to increase the powers by 1 again, so x to the power of 3 becomes x to the power of 4. We need to divide by 4. We're already dividing by 3. Divide by 3 and 4 times together, we get 12. Then we're taking away that, so put the takeaway sign in. We go to the second term. X squared is going to become x cubed. We're going to divide by the 3. We're all dividing by 2, so 2 times 3 is 6. And we're taking that away. And so now we've got our full expression for integration by parts. Now, there's things we can do here. So you can expand the brackets. You could try and factorize things. There's other options from this point onwards. But what we've got here is the kind of essence of how you integrate by parts. And yes, there might be then some manipulated algebra afterwards. Last thing to remember, that when you do this, we're going to get the plus c because we're integrating. So we've got to include the plus c. We also have integration by substitution. So this is when normal integration, you terms separate by a plus or minus. If there's multiplication involved, perhaps brackets next to each other, integration by parts. If you have powers, it's going to be integration by substitution. So you could have something like y equals, then we could have 3x plus 2 cubed. And we want to integrate this. So here's how we do it. So if the integral, if we have a function of gx multiplied by g dash x, then we can say that that's equal to the integral of the function of u. So the f part, we're going to call it f of u because we're going to take out what's inside the brackets as a substitution. So that's going to be our bracket and it's cubed. Then we've got our g of x, that's what's inside the bracket. It's 3x plus 2. And this is also the same as u. Now we need in the form g dash x. So if we differentiate it, we're going to get 3. Now, what this formula means is you can only use a shortcut and change that kind of complicated bit on the left to the simpler bit, f of u, on the right. You can only do that if you've got g dash x in here. And we don't. We don't have a 3 on the outside of this bracket. So we need to put it in. So if we go back to our original statement, we want to integrate 3x plus 2 cubed. And we can only use the integration by substitution if we are multiplying this by g dash x, which is 3. So we're going to put it in. So we get our integral. We've got 3x plus 2 cubed. So really, we want to multiply it by that 3. Now, how are we allowed to do that? Well, there's a way we can do it, because obviously if you multiply by 3, we've now got something 3 times bigger, and it's going to mess up the answer. But if we also put a divide by 3 in here, it's now going to work. because they're going to cancel each other out. And now we can use the integral of f of u. So that's what we're going to do next. So the integral of the function of u, we've actually done the function of u, so we can substitute that in, and it was u cubed. So if we differentiate u cubed, we need to increase the power, so the 3 becomes a 4, and then we're going to divide by the new power. And of course we get the plus c because we integrated. Then we can substitute u back in. U was equal to g of x, which was over 3x plus 2. We also need to remember that we had the third part of this. We've got to put the third in. That means we've got a third multiplied by a quarter. If you multiply those together, you actually get 1/12. So our final answer is going to be a 12th of 3x plus 2 to the power of 4 plus c. And again, at this point, there might be brackets to expand, there might be factors to take out, there might be more steps. But we've done the integration using substitution. Integration is finding the area under a curve. It's particularly between a curve or a line and the x-axis. Now, if you look at the diagram here, it's not between a curve or a line and the x-axis, it's in between a curve and a line. So how can we integrate this? No, it's just as simple as combining the two lines together because both lines are equal to y. So x squared plus 12x plus 32 is equal to y, and x plus 8 is equal to y. So they're both equal to y, then they're both equal to each other. So x squared plus 12x plus 32 is equal to x plus 8. Now what we can do now is combine this all onto one side. So we can take x away from both sides. 12 to take away is 11x. And we can take 8 away from both sides. 32 take away 8 is 24. And now they're combined together. Now we can integrate that. So we can integrate x squared plus 11x plus 24. And if we integrate this combined line, then it's going to give us the area in between the two lines. So to integrate it, we are going to increase the power. So x squared becomes x cubed and divide by the new power. X becomes x squared, divide by the new power. And 24, there's no x, so we're going to put an x in. So now we've got something that represents the area. And all we need to do now for this expression is to use a definite integral. And it's going to be in between the x coordinates we're given. Because we look at these, -3, if you look at the graph, is the end of this curve. And -8 is the start of this curve, or at least the shaded area. So we do the definite integral. So we're going to substitute the largest number first, which is -3. That's going to give us a third of -3 cubed plus 11 halves of -3 squared plus 24 lots of -3. Now I could write the plus c down, but the next step is going to take away the substitution for the smaller number, which was -8. And so we're taking away, we get a negative c out of this. So the c's are going to cancel out. So we can safely ignore them. So we're going to have a third of -8 cubed plus 11 halves of -8 squared plus 24 lots of -8. And if we work all of this out, then we're going to get an answer for the area. So -3 cubed is -27. And then divide it by 3, because we want a third of it. That's going to give us -9. -3 squared is 9. We want 11 halves of it, so times by 11 divided by 2. That's going to give us 49.5. They want 24 times -3. That's going to give us -72. Moving on to the second bracket, we're going to take this bracket away. -8 cubed is going to give us -512. And we want a third of that, so we divide by 3. That's going to give us -170 and 2/3, say 0.6 recurring. Now we need to take this away. It's already negative, so that'll give us a double negative. It'll be positive. Then -8 squared is 64. Well, 11 halves of it times by 11 divided by 2. That's going to give us a positive 352. We're taking away this, so we're going to take it away. Then we've got 24 times -8. It's going to give us -192. And again, we're taking this bracket away. It'll be a double negative, so we're adding it. So we can add all this together for our final answer. -9 plus 49.5 minus 72 plus 170.6 recurring. Take away 352 and add 192. Altogether, that's going to give us a -20.8 to 1 decimal place. Now, how can we have a negative area? Well, we can. So when you get a negative area, you can just assume it's positive. So you can ignore the negative sign. So going back to the graph, we're saying the green highlighted area, we've got 20.8 squares shaded in to 1 decimal place. You can also use this method, find the area under a curve, for when you have a quadratic and a cubic, and the intersection creates 2 separate areas, which I'll label. We've got area number 1 and area number 2. There's a similar method, but there's one important difference partway through. Now, I need a lot of space for this method, so I'm going to try and compress combining the 2 things together. So I'm going to use the cubic as a base. We've got x cubed. Now, with the squared bit, negative 10x squared, we've also got a positive x squared in the other one. So we need to take away x squared to combine them. So it'll be negative 11x squared. Then we've got the 29x, and we've taken away 5x on the other side. So we have to add 5x to both sides to get rid of that. So that would be 34x. Then with the numbers, we've got negative 20. Plus 4 on the other side, we have to take 4 away from both sides, giving us negative 24. So this is what we're going to be integrating. So if we integrate it, increase all the powers by 1, x to the power of 3 becomes x to the power of 4, and divide by the new power. X to the power of 2 becomes x to the power of 3, divide by the new power. X becomes x squared. Now dividing 34 by 2, that should give us 17. And then the 24 is going to become 24x. And as usual, we're going to have the plus c. Now, what's different here is what the definite integral is. Now, we look at the x coordinates, we've got 6, 4, and 1. What we're going to do is do a definite integral for each area one at a time. So for the first area, we can see it's in between the 1 and the 4. So the definite integral for this is going to be, we're going to substitute in the largest one, which is the 4. So we're going to have a quarter of 4 to the power of 4, take away 11 thirds of 4 cubed, plus 17 lots of 4 squared, minus 24 lots of 4. We take away from that second number, which was a 1. So we're going to have a quarter of 1 to the power of 4, take away 11 thirds of 1 to the power of 3, plus 17 lots of 1 squared, minus 24 lots of 1. So there's a lot to do there, but we need to get a number for the first area. So we have 4 to the power of 4, and then a quarter of it divided by 4, will give us 64. 4 to the power of 3, 11 thirds times by 11 divided by 3 is going to give us 234.6 recurring. 4 squared is 60, times it by 17 is going to give us 272. Then we're going to take away 24 times 4, which is 96. Moving on to the second bracket, and remember that we take this one away. So we're substituting 1 and we do a power to 1. We're still going to have 1. So a quarter of 1, that's going to give us negative a quarter. 11 thirds, it's already negative. We're taking it away, it's going to be double negative. Then we've got the 17, positive. We need to take it away, it'll be negative. And then at the end, we've got the 24. So it's already negative, we're taking it away. That's going to become a positive. So we can add all of this together to get the first area. So 64. Take away 234.6 recurring, plus 272, take away 96, take away a quarter, 1.25. Then we're going to add 11 thirds, so add 11 over 3, take away 17, and add 24. All together for this, I'm getting it's 15.75, or 15 3/4. Now, what we need to do now is what we found there, that's only the first area. We need to find the second area. And so we're going to do another substitution. So the second area is in between 4 and 6. If you look up at the top, that's the end point. So the largest one is 6. We're going to substitute in a quarter of 6 to the power of 4. Take away 11 thirds of 6 cubed, plus 17 times 6 squared. Take away 24 times 6. Then we're going to take away the smallest one, which is the 4. Now we've already substituted in the 4. So we can already get a value for this. And it was the first 4 terms. So it was the 64, take away 234.6 recurring, plus 272, take away 96. So that actually was 5 1/4. So we've already got the value for that. So all we need to do now is our third substitution for the 6. So we have a 6 to the power of 4. What, a quarter of it divided by 4? That's 324. 6 to the power of 3, what, 11 thirds of it times by 11 divided by 3. That's going to give us 792. 6 squared is 36, times it by 17. That's giving us 612. And then 24 times 6 is going to give us 144. We're going to take away from that the 5 1/3. And then altogether, that should give us the second area. So 324, take away 792, plus 612, take away 144, take away 5 1/3. That's giving us negative 5 1/3. Isn't it odd that we get that same number twice? Basically, everything, when we substitute in the 6, seems to have cancelled itself out. So for areas, we only take the positive, so it's 5 1/3. That's the second area. So now, if we want the total area, we just need to add those together. So 15 3/4 plus 5 1/3. That's going to give us, so you can write it as a decimal, it'd be 21.1 to one decimal place. Or if you want an accurate answer, you could write it as a fraction. It's 21 1/12 for an accurate unrounded answer. To be careful here, the biggest source of error is that that second area is listed as negative, but you treat it as a positive area. Areas are always positive, so make sure whatever numbers you've got, you make them positive and you add them together at the end. Vectors give a direction and they give a length. So on the first diagram, we can go from A to B, and we can see it's labeled vector A. So we have two A's there. So the capital letters, the points, you can see, the coordinates, the positions, the vertices, whatever you want to call them. And A with a lowercase a is the vector. So we can say the vector from A to B is equal to A. Now, the thing with vectors is they're not limited to particular positions. So, for example, from C to D, you'll notice that's the same length and it's the same direction as A to B. So what we can do is we can say, well, C to D is also equal to A. You'll also see vector B. So from A to E, we can call that vector B. And what we can do as well is we can go backwards. So we can go, let's say, from M to I in the opposite direction to B. But you'll see, other than it being going in the opposite direction, it's otherwise the same direction and the same length. And so what you can do is we can say that the vector M to I, so the direction is really important. We're not saying I to M, we're saying M to I. We can say this is negative B. It's going in the opposite direction. Another thing we can do is use multiples. So for example, we could go from F to H, and we'll see from F to H, we've gone the same direction as A, and we've not gone the same length, we've gone twice as much. The length is twice the length of A. So we can say from F to G is equal to 2A. So we can do maths with the lengths. We could do the same thing with B. So let's say we go from G to O, then vector GO would be equal. You see, again, same direction as B, but it's twice as long, so we call it 2B. If we want to go the opposite direction and go from O to G, then we call it negative 2B. Another thing we can do is we can go halfway. So we could go from, let's say, N halfway over to O. So we can see it's the same direction as A, but it's half the size. So the vector from N to O is equal to half of A. You can also do combinations of vectors. Let's say we wanted to go from, let's say, from M to J. Now, there's no vector labeled for that direction. What we could do is we go from M to I, which is already labeled, and then go from I to J, and we can go the long way around. And this is allowed in vectors. So then we're saying the vector from M to J is equal to, so it was a negative B from M to I, and a positive A from I to J. So we can combine vectors together as well. Our second diagram has got different vectors. It's got a different layout. So it's still from A to B, it's still going to be vector A. So that's the same for this diagram, just by coincidence. But if we have a look at vector B, you'll see that this one's different. It's a slightly different direction as well. So we go from A to O, this time that's vector B. A to O in the previous diagram would have been, something completely different. So just like algebra, the value of the letters can change depending on the question you've got. They're not always constant. Now, you'll notice we have another direction we can go in. We can go from B to O. And from B to O, there's no labeled vector. So we can't immediately label it anything. We can't just say, oh, we'll call it vector C. You're not allowed to do that. You can only use what you've been given. So what can we say about this? Well, we could go the long way around. We could go from B to A, which is the wrong way down vector A, so negative A. And then we can go from A to O, which is the right way down vector B. So we're adding b. So again, with vectors, you can go the long way around if you need to. You'll also notice if we, for example, went from b to c, that's plus b, and c to o is negative a. So even if we went a different direction, we would still get exactly the same answer. So now we know what b to o is, which is negative a plus b. We can start to use it to find other vectors. So let's say you wanted to go from C to E. The direct route doesn't have any lines labelled, so we can't take a direct route. But what we could do is we could go from C to D, and we can go from D to E, and that'll get us to the same endpoint. Now, C to D is the same direction and the same length as B to O. We could even write this with a little equation, so we could say that C to E is equal to C to D plus D to E. So we know that C to D, being the same as B to O, will be negative A plus B. And we know that D to E, it's the opposite direction of A. So then altogether, that's going to give us negative 2A plus B. So you can start to do maths with vectors as well. You'll also commonly see positive vectors put first. So minus 2A plus B, you might see B minus 2A. It represents exactly the same thing, but putting a positive number at the front just means that you don't need to write the positive sign down, because if there's no symbol at the front, we assume it's positive, so we're just saving one space by writing it that way around. You don't get extra marks for it, but you might see it written that way in mark schemes. Now, there's multiple ways of writing vectors. So for example, here we've got vector P and we've got vector Q. And so just using the single letters is just like what we looked at on the last revision slide. But we can split them apart into I and j vectors, and these give us a bit more of an idea about what the direction of the vector is like. So let's sketch out what these things mean. So I corresponds to the x coordinate and y corresponds to j. So when I say 10i, what you mean is that we are going across by 5. When we say 4j, we mean that we're going up by 4. Now, it doesn't mean go across and then go up. What it means is that you're going to go directly in between the 2 points. But rather than describing it as a diagonal line, we describe it as a horizontal and a vertical component. So we've got vector P, and we've got the measurements of vector P, which is what 10i and 4j basically give us. Now, what about vector Q? So vector Q, we can see it's 4i, so it's going to go another 4 across, and it's negative 9j, so it's going to go 9 down. So the plus and minus just tell you it's going left or right or up or down. So now we can label vector Q. So it's going to go directly. It's not going to go left then down. So it's going to look like this. So we've got vector P, and at the end of vector P, we've got vector Q. Now we can do more maths with this. So for example, we could have vector P plus vector Q. And so to do that, we take vector P, 10i plus 4j, and we take vector Q, 4i minus 9j, and I'm going to add those vectors together. So 10i plus 4i is 14i, and 4j take away 9j is negative 5j. Now, we can also show this vector on the diagram. So P plus Q, we're going to start at the start of P, and we're going to end at the end of Q. So again, it's not like a complicated web of instructions. We do 10 different instructions. You go right and then up and then right and then down. What you're actually doing is you're going directly from the start of P to the end of Q. And so P plus Q is what I'm labeling in pink. So again, there's a distinction between what the vector actually does, which is a direct route, and the way it's written, which might be giving you vertical and horizontal measurements to give you an idea of where the vector actually points. Now, we can also do multiples of these like we did with the previous vectors. So if P plus Q is equal to 14i plus 5j, then we can say that 2 lots of P plus 2 lots of Q, that's going to be something like 2 lots of 4i minus 5j. In fact, you might actually write the original expression using brackets as well. So you can write them out in ways like this. You can expand the brackets as well. So the brackets are just a good way to show what you're going to do. So 2 times 14 is 28. 2 times 5 is 10. And so 2 lots of P plus Q would be 28i minus 10j. If we were to draw that out, then what would happen is we would get something like this. And so it would extend out further on. It would be twice as long. Now, I and j vectors are called position vectors, and we can use them to draw shapes and also prove things about shapes. So we're looking at a parallelogram. Let's try and draw the parallelogram first. So these position vectors, they all come from the origin. They come from, the point we're measuring everything from. So let's call the origin O, and let's try and draw all the different vectors. So vector A is going to go minus 2i, so 2 to the left, and plus 4j, so 4 up. So here is where point A is going to be. So the position vectors have just given us an idea of the direction that vector A goes. Next, we're going to look at vector B. So it's 8i, so 8 to the right, and 3j, so 3 up. And again, the vector just gives us the direct route. So 2 components just give us the length of it in both directions. Then let's look at C. So C is negative I, and then it's plus 10j. So it's going to be something like here. And again, it's giving us the direct route. The last one for D, so it's minus 11i and plus 11j. So it's going to be somewhere around about here. And so the vector is going all the way over here. So we can see, it looks like a bit of a mess at the moment. So we've gone from the origin in 4 different directions. And we're saying this is a parallelogram. So let's see if it does make something that roughly looks like a parallelogram. So we're going to go from A to B, from B to C, C to D, and A to D. And we can see, it could be possible that this is going to be a parallelogram. Now, I've sketched this out. I do have a grid here that you can't see, so it is kind of vaguely accurate as well. But you can get the idea of where all the different vectors are going to and how it's describing where the shape comes from. The next step is, how do we prove that it's a parallelogram? So for the proof, what we need to do is we need to show that the opposite sides are equal. So A to B should be the same vector as C to D, or it's going to be in the same order, so from D to C. So I'm just going from left to right here. So be careful which way around the letters are. So if they're the same length and the same direction, then they must be parallel. The same thing for the 2 sides, so we need to have A to D would have to be the same as B to C. So we need to look at what these vectors are. So let's look at A to B first. So to go from A to B, we can't go the direct route. There's no vector label there. But there is a vector from A to O that was negative A. And there is a vector from O to B that was positive B. So if we had the labels now, we're going negative down A, and then we're going positive up B. We also had vector C and vector D as well, which we'll need later. So what's negative A going to be? Well, we've already got A. It's negative 2i plus 4j. So the negative version of that, we're going to flip the signs. So it's going to be 2i minus 4j. Then we want to add B onto that, which is 8i plus 3j. So if we add all this up, like terms, 2i plus 8i is 10i. Negative 4j plus 3j is negative 1j. So that's what AB is. So now let's have a look to see if it's the same direction and the same length as D to C. So to start at D and end at C, we can't take the direct route, but we can go via the origin because that's what the position vectors have given us. So we can go backwards down D to get to the origin and then go forwards up C to get to C. Negative D, flip the signs on D, it's going to be 11i minus 11j. And then C, what a positive C, so it's the same one that's written down, negative I plus 10j. So collect like terms again, 11i minus I is 10i. And negative 11j plus 10j is going to be negative 1j. And what you can see here is that the vectors are the same. They're both 10i minus j. So if AB and DC are equal to the same thing, that means, therefore, they are parallel. So we've proven one set of parallel sides, and we can use the parallel notation on this as well now. These are definitely parallel, and they're also the same length. So what we need to do now is follow the same process to see if A to D and B to C are also the same length. Now, I'm not going to do that because I think we've revised this enough now, so you should know what to do next. So you can have a go at that yourself, and you should be able to get the same answer for AD and BC, but it is actually a parallelogram. If it's saying prove it's a parallelogram, then it is going to be a parallelogram. If it says something like, is it a parallelogram? Then it not being one might be an option, and then you'd prove it by showing that these answers are different. So just be careful with the wording of the question, because you made a mistake here, and they didn't appear to be parallel, and it's saying prove it's parallel, you should know that you've made a mistake and you need to go back over your working out. Another thing we can do with vectors is collinear lines. All this means is that it's a straight line. So again, we can try and sketch this out. If you've got a grid, you can do this accurately. So starting from the origin, A is 1 to the right and 2 up. B is 7 to the right and it's 2 down. And C is 10 to the right and it's 4 down. So we have the vectors for these, O to A, remember it's a direct route, O to B, and O to C. Now, looking at A, B, and C themselves, if they're collinear, then they're going to be a straight line. So let's see if they actually are a straight line. So join up A all the way over to C, we should have B stop off in the middle. And we can see, since I've drawn this accurately, you can see they are actually all on a straight line. However, you're not always going to have some graph paper to do this accurately on. So we need another way to prove that they're all on a straight line. And again, it's going to be by looking at the values of the vectors. So what we want to do is we want to look at vector AB and we want to look at vector BC. And there should be something about the two different sections of the line that tells you that they're straight. So let's look at A, B first. So to start at A and end at B, it has no vector in between A and B. But we could go from A to O, which would be minus A, and we could go from O to B, which is plus B. The negative vector of A is negative I minus 2j, and the positive vector of B is 7i minus 2j. Add up the i's, you get 6i, and add up the j's, you get negative 4j. Now let's look at BC and see if there's anything we can compare. So B to C, we can't go direct, but we could go backwards down B to the origin and then forwards up C to get to C. Negative B is negative 7i plus 2j, and positive C is 10i minus 4j. So collecting like terms, negative 7i plus 10i is going to be 3i. Then looking at the j's, 2j minus 4j is going to be negative 2j. So looking at the two answers, they do appear to be different. So how can we say they're on a straight line when the vectors are different? Well, what we can do is you can try factorising them. Now, if we factorise AB, we can take 2 out of both, and that'll give us 3i minus 2j. And that's actually the same answer that we had for BC. So we can see the actual I and j bit is the same length and the same direction. It's just that AB is multiplied by 2 as well, which means that AB is twice as long as BC. So we're proving something's a straight line. They don't need to be the same direction and the same length. A straight line, they're only going to be in the same direction. And so you only need to look at the direction bit. The directions don't match up. Have a look to see if you can factorise to make the directions match up. The only rule with that is you can't have any bits of I and j outside of the bracket. The bracket bit has got to be exactly the same. At the end, we can just write AB and BC have 3i minus 2j as a factor. Therefore, they're a straight line. They're collinear. Position vectors give a vector in terms of a kind of x and y length. You can also have vectors written like this diagram where we have the length of the vector and we have an angle of the vector. Now, one thing you might want to do is you might want to change this into a position vector. So it might be that we want to know how far across it is, which is going to be our I vector, and we want to know how far up it goes, which is going to be our j vector. So how do we do it? Well, you might notice you might be able to draw this as a triangle. So we have a hypotenuse, 11.7. So that's a total length of the vector. We want to get j and I. So we can write I here, and we could write j on the other side of the triangle. It's going to be the same length. We also know the angle this is at. It's 42 degrees. Now, given this is going to be a right angle that's on a coordinate grid, you know, I and j are at right angles to each other, like a x and y axis are, then we can use trigonometry for this. We can label the sides. Again, we've got the hypotenuse, we've got the adjacent, and we've got an opposite. So we can use SOHCAHTOA. We're going to want a formula triangle for this. And we can't find them both at once. We can only find one at a time. So let's try and find the I first. I realize I label them both I. Let's make sure the one in the y direction is going to be a j. So with I, that means we've got the adjacent and we've got the hypotenuse as a clue. So it's going to be a car question. So write car in the formula triangle. And we're looking for what the adjacent is. So if we don't have the adjacent, we've only got the cosine and the hypotenuse. So we need to multiply them together. So it's going to be the cosine of the angle 42 degrees, multiplied by the hypotenuse 11.7. And if we do that calculation, we're going to get the kind of distance to the left that I goes. So cos 42 multiplied by 11.7 gives us 8.69 to 2 decimal places. Now let's have a look at J. So again, we're going to do the same thing. We're going to need a formula triangle for J. We're looking for J, that's the opposite. We've got the hypotenuse as a clue. It's going to be a SOA question. We're looking for the opposite, so it's going to be sine times the hypotenuse. So sine 42 times 11.7. Now, if you just look at the two calculations, notice they're quite similar. So you can reuse your previous calculation, it's on your calculator screen, by pressing the back button and swapping cos for sine. What you should get is 7.83 to 2 decimal places. So now we can write this out as a position vector. So I is 8.69 and J is 7.83. Now, the last thing to do here is if they're going to be positive or negative, because it all depends on where the angle is measured from. Now, if the angle starts measuring from the positive x side, then it's going to give you its negative or positive already, so you don't need to think about it. If it's from the negative x-axis and it doesn't go anti-clockwise, it's going to go maybe clockwise from here or anti-clockwise from here, then we need to be looking ourselves if it's positive or negative. So out of the 4 possible directions you can measure from the x-axis, if you're going from the positive side, anti-clockwise, it will give you positive or negative. If it's going in the other directions, then you need to be looking if it's positive or negative yourself. If the angle's measured from the y-axis, then what you need to do is take it away from 90 to kind of make it so you've got the kind of equivalent angle from the x-axis. These have to be measured from the x-axis. Now think about the quadrants of one of these. X is positive on the right-hand side, and it's negative on the left-hand side. Y is positive at the top, and it's negative at the bottom. So you just look at which the 4 quadrants are in, and we can see the quadrant we're in is the top left, which means that X is going to be negative, so I will be negative, and J is going to be positive. So our final answer for the position vectors is negative 8.69i plus 7.83j. What we have here is a column vector, and you can rewrite it as a position vector. So it'll be 8.23i plus 11.33j. So with a column vector, the top one is x, the bottom one is y, x is I, and y is j. Now, what if you wanted this to be a kind of total length and an angle, like the last bit we looked at? How do we know the angle of this direction? How can we find it? So again, it's going to be about triangles. So you can imagine we've got the I vector, or the I part of the vector, 8.23. We've got the j part, 11.33. And so the total length of the vector is going to be from the start of I to the end of j. And we call this the magnitude, which we label r. We're also going to want the angle of this, which we're going to call theta. So how do we find these two things? It's really easy. We've got 2 sides of a triangle. And what the hypotenuse of a triangle? It's Pythagoras' theorem. So we're going to square the 2 sides. We're going to add the answers together. And then we're going to square root that answer to get the hypotenuse. So you can type all of that into your calculator on one line. I'm going to do it in 2 actually. So I'm going to write out the squared bits and add them. And then I'm going to square root the answer. You want to write it in one line, you write square root first, and then you put brackets around everything that's been square rooted. When you do that, you should get the answer, which is 14. Now it's 14.0036, so to 1 or 2 decimal places, it's going to be 14. So that's the magnitude of the vector. It's the length of the vector. So we've got an x length, a y length, and then the total combined lengths. So next, what about the angle? How do we find the angle? Now, again, it's going to be using trigonometry. So we've got the hypotenuse as r, the adjacent is 8.23, and the opposite is 11.33. So we're going to need a formula triangle. We're going to use SOHCAHTOA. Now, we have O and A as clues. So it's going to be a TOA question, and we're looking for the angle. So we can see we've got O over A. That means that the tan of the angle is equal to the opposite, 11.33, over the adjacent, 8.23. So solve the equation. It needs to do tan to the minus 1 to both sides. Get theta on its own. It's going to be tan to the minus 1, 11.33, over 8.23. That can be typed into your calculator. Remember to open the brackets, that's really important. Divide the numbers by each other. Close the bracket, and you should get 54 degrees. And that's actually 54 to one decimal place as well. So now we know from the column vector 8.23 over 11.33, we know the total length of the vector, the magnitude of the vector, which is 14, and we know the direction it's going in. It's going at 54 degrees from the x-axis.
Ouch! This is why in some videos I have unexplained scratches.